everyone, and welcome to another video. Today we are on to our second video in our three-part series focusing on introductory wind tunnel testing. If you've been following this series, you know that in our previous video we took a virtual tour of the Kirsten Wind Tunnel at the University of Washington and talked about how a wind tunnel acquires aerodynamic force and moment data for an aircraft. This data acquisition is actually the first step in the process of leveraging a wind tunnel for aerodynamic engineering design. So today I'd like to discuss the next step in the process, where we're going to discuss how to take the raw data we acquired in step 1 and then manipulate and transform it to better represent a full-scale free flight aircraft configuration. So today we're just going to focus on the set of transformations that are applied to a single data point. In our third and final video, we'll take a look at interpreting some of the results you might see from a wind tunnel, as well as provide some further food for thought regarding wind tunnel testing. So if that sounds like fun, let's go ahead and get started. So if we follow the procedures outlined in the data acquisition video, we can obtain some aerodynamic force and moment data for this aircraft model in the wind tunnel. Now, it might be tempting to take this data and immediately start using it for downstream engineering analysis or design. I mean, you probably got those pesky GNC engineers banging on your door, begging for your aero data so that they can drop it in their dynamic aircraft simulation. However, if you think about it long enough, the ultimate goal is to produce data that's representative of free flight conditions, which are actually a little bit different from the wind tunnel conditions. So, for example, there's a major geometric scaling difference. You know, in other words, what I mean is the model, right? It's only 2 to 3% of the size of the full-size aircraft. It's also probably made out of solid aluminum, so its weight distribution and therefore its CG is probably completely different of the real aircraft. Moving down to the underside of the model, notice that we've got this strut attached to the model, which is also attached to the balance. So any forces that are on the strut are actually going to be recorded. We also have this fairing, and while this isn't really attached to the balance, it's still changing the airflow underneath the model. In a similar fashion, we've actually got walls also on all sides of the model, which will also affect the airflow around the model. So, the question now is, given these discrepancies, how do we correct the wind tunnel data to free flight conditions? Well, this is what the data reduction process is all about, and it's what we're going to discuss today. So what I'd like to do is cover the data reduction process that was in place when I worked at the Kirsten Wind Tunnel in the early 2000s. And as such, I guess some of this information might be a little bit outdated, but I think it's still relevant and useful. And again, this isn't a comprehensive list of all the corrections, as different tunnels might have different procedures, but I hope this is going to give you an idea of what types of corrections are typically made to wind tunnel data. So what we're going to do is we're going to cover 11 different corrections/steps today. So we'll start off by talking about the indicated to actual dynamic pressure correction. We'll then move on to balance interactions, then discuss strut tears, and also tears and interference. And also another type of tear is weight tears. We'll then discuss moment transfers, blockage corrections, and that gives us enough information to basically generate some initial coefficients. If we want to keep on going and further correcting the data, we can go and talk about flow angularity, namely crossflow and upflow, as well as wall corrections. And if you do all of that, you pretty much have enough information at this point to produce what we determine and call final coefficients and a corrected angle of attack. And then lastly, what you can do is you can do axis transfers and change those to different frames if you'd like. So again, this is our 12-step process that we're going to go through today. So why don't we just go ahead and get started on step A, which is our indicated to actual dynamic pressure. Okay, so the first correction has to do with measuring the dynamic pressure in the test section, and we need to be able to do that accurately. So maybe that begs the question, how do you measure dynamic pressure in a wind tunnel? So here's a side view. know, so again, air is coming down the bell mouth. It's going to get, the area decreases until it reaches the test section, which is a constant cross-sectional area, and then it expands again into the diffuser. So as you can imagine, the air is kind of going slowly here, then it is going to accelerate through the test section and then decelerate again, right? So that's the idea. And what we really want to know is, I would like to know what is the dynamic pressure, or effectively the velocity of the wind here in the test section, okay? So the way this is actually done is, let's go ahead and measure and mark two stations. So one station is here at the bell mouth, okay, and then the second station is at the front of the test section where the cross-sectional area starts getting constant. So let's label these. Maybe here's station 1. So let's call this cross-sectional area A1, and then this cross-sectional area here at station 2, let's call this A2, okay? And what's really interesting about this is, if you were to go to the Kirsten wind tunnel, or you know, other wind tunnels actually use this technique as well. If you were to go there and look on the floor and the ceiling, right here and here, as well as over here and here in blue, there are going to be these little strips on the floor. So these strips are basically metal strips with a lot of little dots, little holes in them. Basically what those holes are, they're basically static pressure ports, okay? So these pressure ports here at the bell mouth, they're all hooked together and plumbed to a single set of lines. Similarly, these static pressure ports are also you know, collected together, so they all average out, and then they all go to a set of lines, and then you can hook these two up to basically a differential pressure transducer. So what we can do is measure the difference in static pressure between the bell mouth and the test section. And let's see if we can somehow now figure out, with that information, basically just knowing the difference in static pressure, can we back out what is the dynamic pressure or the airspeed here in the test section, right? Okay, so to do that, let's just go ahead and take a look at this. So again, you've got velocity here, the wind at this location is going at speed, let's call it V1, and then here it's going faster at V2, okay? So I think at this point we have enough information to write basically the continuity equation, which is basically a mass flow conservation, right? So let's write continuity equation, right, which is basically conservation of mass. Right? So if we look at the volumetric mass flow rate here at station 1, we have the air density, right? So this is, let's call it rho 1. Rho 1 times the cross-sectional area A1 times V1, right? So again, if you want to just work this out in your head, so what's the air density here? This is in, you know, kilograms per meter cubed. The cross-sectional area is in like meters squared, and then the velocity is meters per second, right? So you basically get what? It's the mass flow rate, right, in terms of kilograms per second of air moving past station 1, right? So that better be equal to the amount of kilograms per second flowing through station 2, right? So we can basically write that's got to equal rho 2 A2 V2. Right? Would everyone agree? Okay, so now, since we're in a subsonic wind tunnel, I think it's safe to make the assumption that this is an incompressible fluid, right? So let's say, assume that we have incompressible flow, right? Meaning that rho 1 is equal to rho 2, right? The air density stays constant, okay? So in that case, basically these cancel, so we can juggle that equation to basically, let's solve for V1, right? So V1 is just going to be V2 times the area ratio, A2 over A1, right? Okay, box this up, we're going to save this and use it for in a second. Okay, what else can we say? We also know that the total pressure is conserved, right? So in this case, total pressure is constant, right? So P total at station 1 has got to equal P total at station 2, right? And again, P total at station 1, it's going to be the static pressure at station 1 plus the dynamic pressure at station 2. So at station 1. What is that? Dynamic pressure 1/2 rho 1 V1 squared, right? Okay, and again, this has to equal the total pressure at station 2, so we have P static 2 plus 1/2 rho 2 V2 squared, right? Okay, so solve this thing for now for V2, okay? And well, actually, here, tell you what, sorry, one more step. Let's go ahead and, yeah, so you can substitute in your V1 expression here, right here, right? So this is, I'm going to substitute this guy in for V1. So I get P static 1 plus 1/2 rho 1, this thing, right? V2 times A2 over A1 squared, right, is equal to P static 2 plus 1/2 rho 2 V2 squared. Okay, now solve this entire thing for V2, okay? And again, the nitty-gritty is you're able to do this kind of manipulation, and we're going to end up with V2 is going to be square root of 2 times P static 1 minus P static 2 all over rho times 1 minus the quantity A2 over A1 squared, something like this, okay? And again, maybe we should note that we made the incompressible flow assumption during this, because you notice here that we only have rho instead of rho 1 and rho 2, so we're just going to assume that rho 1 is equal to rho 2 is equal to rho, right? So it's incompressible, right? Okay, so great. At this point, look at this. This is pretty darn handy, right? Because if you think about this long enough, this is giving us the airspeed at the test section, right? And what do you need to know? You need to know the difference in P static 1 and P static 2. That's exactly what this differential pressure transducer is going to directly measure, right? It's going to give us the difference P static 1 minus P static 2, right? Okay, what else do we need to know? We need to know the air density, so we can obtain that if you take a temperature reading in the morning or whenever you're going to run the tunnel. You can get the temperature and calculate basically what is the air density for the given day of testing, and then 1 minus this thing, A2 over A1. Again, if you look at this, this is just the area ratio between the test section and the bell mouth, and that is a constant number, right? These areas are not ever changing. So you figure that thing out one time for your tunnel and you're basically good to go. So shebang, we've basically got the airspeed at the test section using this technique, okay? And again, what you could do is, again, you know, most times, most wind tunnel engineers and test engineers, we don't really like to talk about velocity. It's much more useful to talk about dynamic pressure. So really what's more interesting is Q, right? Which is really Q at station 2. I want the dynamic pressure at the test section. That's what we're really interested in. So this is just gonna be 1/2 rho V2 squared, right? So just jam this expression in here, and I think this comes out actually quite nicely. This is just P static 1 minus P static 2 all over 1 minus the area ratios squared. Okay? Okay? So, the only other thing that we'll maybe mention here is maybe what we should do is we should put a subscript on this. Let's call this QI, as in this is the indicated dynamic pressure, right? This is the dynamic pressure that you can calculate if you have this static, if you have these static strips on your tunnel, right? So this is going to allow us to calculate Q indicated, right? Via this technique, right? So we can get what we think is the dynamic pressure here. Now the reason I say that is because we should ask ourselves, is there another way that we could measure dynamic pressure in the test section, right? So another way to go about this is you could stick in, remember in our data acquisition video, we talked about how the Kirsten wind tunnel, you can introduce probes into the test section, into the ceiling. So one thing you could do is you could go ahead and you could put a probe, like a total pressure or a pedostatic probe or a 5-hole probe or something like that, and you could basically obtain another independent measurement of dynamic pressure, okay? So let's call this Q The reason being is that this technique of using a probe to find out what the dynamic pressure is exactly at any location in the tunnel is actually a lot more accurate than this static pressure scheme, right? And I guess a lot is kind of, there maybe is an asterisk that needs to go along with that. A lot, that's a relative term. In fact, I'll direct your attention, here's a paper that the Kirsten Wind Tunnel actually published in 2019 talking about, they did this, they stuck a probe in the test section and they moved it all around to try to understand what does the flow characteristics look like in the test section, and they get different numbers in terms of what this probe measures as the actual dynamic pressure, right, QA, versus what the differential pressure transducers measure, right? That's this QI. So you might say, okay, well, if this probe technique is more accurate, why don't you just use that all the time, right? Well, the reason you can't use this probe all the time is because what's usually sitting here in the test section? Usually you've got this fairing here, you've got your aircraft model sitting in here, so you can't have this probe in, right next to the model or in front of the model disrupting the flow. You basically can't use this probe during a normal test. However, this differential pressure transducer system with these static ports on the floor and the ceiling of the tunnel that's incredibly unintrusive, right? It's just sitting there. You could have that all the time. It's not influencing the flow. So this is how we are going to measure the dynamic pressure, right? We are going to go ahead and get QI, even though we know that it's going to be a little bit different than what the actual dynamic pressure is, QA. Well, you know what? If we understand these two differences, we can just come up with a correction factor, right? If I understand that, oh, these differential pressure transducers, they always read, low by 2%. Well, what we should do is calculate the actual dynamic pressure. So what's typically done is we say that the Q actual is going to be, and I'm using a bad notation here. Maybe, well, okay, let's leave it like this. So, okay, so this is the thing we can get from the differential pressure transducer system. This is what we know it should be. So there needs to be a correction factor here, some term like, I don't know, you call it eta or something like that, right? Some number near 1, which is going to tell you how much you need to kind of fudge factor your indicated dynamic pressure to get something that's close to the actual pressure, right? So this term is sometimes referred to as maybe not the most innovative way. This factor is called QA over QI, right? It's just a conversion factor that is, again, near 1. So again, you conduct your test section survey using the more accurate pedostatic probe or 5-hole probe that tells you what QA is. At the same time, you measure what does your static pressure system measure, that's QI. And if the two are not exactly equal, you basically just cook up a conversion factor that's near unity to account for the differences. So that's yeah, that's pretty much it. So this is one correction that you're going to need to do, which is due to the fact that you're measuring a dynamic pressure using a system which is slightly less accurate than what you actually want, right? Yeah, and while we've got this picture up, let me talk about one more pressure kind of quote-unquote correction. Is if you think about this, right, with your normal aircraft in free flight, right, it's just flying around outside at some velocity v, right? The static pressure is 1 atmosphere, right? Assuming you're flying near sea level or something like that, right? Or maybe we should say this is approximately 1 atmosphere, right? Right? Would everyone agree? This is in free flight. So what's interesting about this is if you look at this diagram, we know that the total pressure is conserved, right? We already just talked about that. So we said the P total at 1 is equal to the P total at 2, right? Now, what is the P total at 1? That's P static at 1 plus 1/2 rho V1 squared. Again, I'm going to make the incompressible assumption here, so I'm just going to call everything rho, right? And then that's P static 2 plus 1/2 rho V2 squared, right? Okay, so now let's make the assumption here that this V1 is small, right? So if V1 is small, if the air is moving relatively slowly here in the bell mouth, this is going to go down to 0, right? So what's interesting here is that out here you have effectively close to 1 atmosphere total pressure, right? So the static pressure in the bell mouth is about 1 atmosphere, right? Okay? But now, over here, in order to have this be conserved, we see that this has got to equal P static 2 plus 1/2 rho V2 squared. So this dynamic pressure bit plus the static pressure at the test section has got to equal about 1 atmosphere, meaning that that your static pressure at in the test section is less than 1 atmosphere. So the model over here is experiencing a static pressure which is not really like free flight conditions, right? So I mean, one way you can get around this, and this is actually what the Kirsten wind tunnel does, and it's actually kind of interesting, is they actually, the reason this occurs, right, is because this is effectively like a Venturi tube, right, where you're basically conserving total pressure, so you're trading off static and dynamic pressure, right, as you accelerate. So one thing that they actually do is they cut a hole in the side of the test section right here. Right? What does this do? What this does is, if you think about this long enough, by cutting a hole in the side of the test section, we're forcing the static pressure in the test section to be 1 atmosphere. So what that hole does is it forces this term at steady state to be about 1 atmosphere. Right? So this is actually pretty fascinating. What this means is that as the tunnel is coming up to speed, right, the fans are doing work on the fluid, it's increasing the dynamic pressure, therefore, and since the hole is keeping the static pressure at about 1 atmosphere, we're actually increasing the total pressure of the entire tunnel, right? Which again makes sense, right? The fans are doing work on the flow, it's energizing the flow, it's giving it more energy, so you have got higher static higher total pressure while keeping the static pressure the same. What's fascinating about this is then as the tunnel comes down, right, like this entire term, the total pressure inside the tunnel, inside the test section is constant. But as the wind speed starts going down, right, as the fans start decelerating, so at the end of a run when the dynamic pressure starts going down, the static pressure inside the test section starts going up. So if the static pressure inside the test section is going up and you're sitting out here at 1 atmosphere static pressure, you'll actually feel air come rushing out of this hole. It's really kind of neat. So if you're standing near the side and the tunnel comes down, you'll feel the air kind of coming out of the wind tunnel due to this effect, okay? So again, this is a little bit of an asterisk side note that's just kind of an interesting thing to note. But also, again, if you're a wind tunnel designer, maybe this is something to think about. Maybe you might want to think about cutting holes in the side of your test section to maintain an approximate 1 atmosphere static pressure. All right, so we're on to our second correction, which is dealing with balance interactions. So what that means is literally the fact that the balance, when you apply some kind of force or moment to the model, it might not read exactly what the force or moment actually is. There might be some interactions or cross-coupling between channels. So, for example, if you were to sit here and somehow apply a pure lift force, okay, and let's maybe use a subscript BU to denote this is like the truth or it's the balance, whatever you want to use it. I'm going to use terminology that you might see again if you were doing data reduction in the Kirsten wind tunnel, but this is what you're actually applying to the balance, right? Now, what the balance is going to do is it's going to read something, and this is going to spit out some raw measurement value. And sure, it's probably going to say that, yeah, there's a lift value, which is approximately probably the value that was applied. But you know what? All the other channels, the drag, the side force, heck, even the pitching moment, the rolling moment, and the yawing moment, these might not be 0. These might be some small number, some epsilon, right? all of these things. You might get some non-zero values in all of these channels. Hopefully they're small, but they're not zero. Meaning, again, here's the problem, right? The problem is you read all of these measurements from the balance, and again, they are not exactly accurate to what was actually applied to the model. So there's a discrepancy here that we need to take into account, right? Which is going to account for these interactions between the channels, okay? So the way we're going to do this is, again, we're looking for now a function, right? Where you tell me all of the measurements that the balance read, which are, again, we're using with these subscript R's. So we're going to get all of the forces. So again, it's maybe we should stack these all up, right? You're going to get lift, drag, side force, as well as the pitching moment, rolling moment, and the yawing moment. And again, I'm using the subscript R to denote all of the forces that the balance measures. And then what we need to do is we need some function which is going to then translate or take care of all of these interactions and basically spit out the lift BU, drag BU, side force BU, pitching moment BU, rolling moment BU, and yawing moment BU. All right, so this is the idea. So this is basically your balance interactions function, right? So for any 6 values, right, that go in, these are, again, are read by the balance. This balance interaction correction or function or matrix or correction, however you want to think about this function will then manipulate them and basically return what are the actual forces and moments that are applied to the model, right? Okay, so the question is, how are we going to generate this function, right? So at the Kirsten wind tunnel, at least the last time I checked, this was done through a second order correction, meaning all of these outputs here. So let's write this in a big 6x1 matrix. So lift, BU, drag, BU, side force, BU, let me see, how did I, pitching moment, BU, rolling moment, BU, and yawing moment, BU. Right? The way these were obtained is you basically take all of the raw measurements that are coming out of the balance, okay? So let's stack these all up in a vector so that you have lift, drag, side force, pitching moment, rolling moment, yawing moment. And again, these all have subscript R's, right? Because these are all of the values that the balance, the raw values that the balance reads, right? Or reports, however you want to think about it, right? And all you're going to do is you're going to multiply this by a 6x6 matrix. Let's call this A1, okay? So here, A1 is a 6x6. And then there's a second order term, meaning you also take all of these raw measurements that the balance spits out. So again, lift, drag, side force, pitching moment, rolling moment, yawing moment. Again, all these are raws, R, right? And you square all of them. This is where the second order portion of the term comes from, okay? So you take all those values, square them, and then you multiply by a second matrix, A2. So in this case, A1 and A2 are basically 6x6 matrices. Okay? Now, in an ideal world, right, A1 would be an identity matrix and A2 would be a big fat zero matrix, right? But if your instrument, if the balance is imprecise and if there are interactions, there may be off-diagonal terms here in the A1 and there may be non-zero, non-trivial entries all over the A2 matrix, right? So the game plan at this point is all we need to do is we need to find out what are the A1 and A2 that are going to make our measurements as accurate as possible, right? So the goal at this point, right, is to find A1 and A2, right? So again, since these are 6x6 matrices, each one of them have 36 entries, so there's 36 unknowns here, there's 36 unknowns here, so really we're looking for basically finding 72 numbers, right, that are going to make this function fit reality, all right? So that's the game plan. The question now you might want to think about is how are we going to go about finding these A1 and A2 matrices? So this is actually a very involved process that's known as a balance calibration, right? So the idea with the balance calibration is we are going to insert or put a rig in the test section that is going to be able to apply very precise forces and moments to the balance, right? So we can then apply these BU. We can apply a force that we know and can measure and is true, and then we'll read what the balance spits out in that scenario. Then we'll change the configuration or maybe change the loading, do it again, change the loading again, do it again. So just as an example, here's a picture of an older version of the balance calibration rig at the Kirsten wind tunnel. So as you can see in this picture right now, I'll let you think about this a moment. Look at this picture and ask yourself, what is this setup going to do when you apply weight? You can see there's these little trays. It might be a little bit hard to see, but on the side there are these trays where we would add known weights to the rig so that we can measure the forces and the moments that are applied. So again, if you look at this picture long enough, you'll basically see that what this is designed to do is it's going to design to introduce a pure rolling moment. So if you were to add weights to this to those two trays, you should be applying a 100% pure rolling moment. And furthermore, you can look at the sign convention, right? The SIGN. This is going to yield, since I think the picture we're looking at it from the diffuser looking up the test section towards the bell mouth, you'll see that this is a rolling moment that is tending to put the right wingtip of the aircraft down. And if you watched our video last week, right, we said that at the Kirsten wind tunnel, the sign convention for that rolling moment is that's a positive rolling moment, right? So again, this particular configuration in this picture I'm showing you here is designed to exactly add and apply a positive rolling moment only to the balance. And what we see in this situation is even though you apply a pure rolling moment, some of these other raw values are non-zero. We get a whole heck of a lot of raw rolling moment, but some of these other channels are non-zero, right? And that's the whole rub with this balance interaction idea, is that you only have the raw measurements. This is what we acquire from the balance, right? This is the numbers that the balance spit out. We need to now calibrate that and take into account this interaction here using this A1 and this A2 to matrix, right? So that's the game plan. That's what we want to do. So with that in mind, maybe what I want to do is I want to simplify this problem right now, because this is the real problem of the Kirsten wind tunnel. If you have a full three force component, 3 moment component balance, you have to deal with these 72 numbers. I'd like to shrink the dimensionality of the problem just so we can talk about it conceptually, and then you can take that idea and generalize it to this larger case. So what I want to consider right now is, let's just go ahead and consider a 3 force component balance. So in other words, I only want to look at X, let's call it XBU, right? This is going to be the actual forces and moments that are, the actual forces that are on this balance. So again, this balance, all it does is it only measures 3 forces. So lift BU, drag BU, and side force BU. Right? Okay, so again, these are known forces applied to balance, right? Again, you can think of these as like the truth values, okay? And then I'd like to talk about the raw values, again, using our R subscript. So this is lift raw, drag raw, side force raw, right? And again, these are values that are read or reported, however you want to think about that, by the balance. Okay, and there is a discrepancy here. So this is a much simpler problem than this. And furthermore, instead of looking at a second order correction, remember the Kirsten wind tunnel, the real wind tunnel, and other wind tunnels might have second order or third order, or however nonlinear their balance is. They might have to have many more terms to correct for this. But again, the Kirsten wind tunnel has a second order correction. Again, that's too complicated for this little toy problem we're looking at right here. So let's just consider a first order correction only. So in other words, what I'd like to look at is I want to look at generating a function which is going to give me the truth values, right, xbu, if it knows what the raw values are reported by the balance. And again, this function that we're going to use for this example is just going to be a similar function to what we did over here. It's just a matrix mapping. So it's a linear mapping between the raw values and the BU. So here, let's call this matrix A. Okay, so in this case, A is, again, it's our interaction matrix, but in this case, it's just a 3 by 3 interaction matrix. Okay, so this problem is a lot smaller here. So we just need to find these 9 values. So again, in this case, the goal is to find A, right? So it's basically just finding these 9 constants. Okay, so that's the game plan. I'd like to look at this simpler problem here and just come up with a couple of ways of how we can find this interaction matrix for this smaller test problem. And then once we understand that, I think it's a short hop, skip, and a jump to basically scale it back up for the full second order problem, because we'll see a lot of this is very similar. So anyway, give me a second to erase the board and let's talk about 2 different ways to go about trying to find this, this A matrix. All right, so let's look at method 1. So again, I've rewritten our interaction equation here. And again, just to refresh your memory, right? A is a 3 by 3 matrix, and both xbu and xraw are just 3-element long vectors, okay? So the other way I guess we could rewrite this is you can solve this, basically move everything to one side, right? So you could also write this as, we could write this as A times xr minus xbu, right, is equal to a 3 by 3, a 3 by 1 0 matrix, right? That's the same way to go about this, right? Okay, so the idea with this method is we're going to go ahead and apply, how about, let's call it test point 1. Right? So test point 1, maybe what that means is you're going to apply on the balance, maybe just like pure lift, right? So maybe let's write this down here as pure lift, right? So in this situation, if there is pure lift, this xbu, right? Right, it's going to look something like, I don't know, maybe like you put 100 newtons of lift and then 0 newtons of drag, 0 newtons of side force, right? I'm just making up these numbers, right? And you're going to then apply this to the balance using that balance calibration rig we just talked about. And what you're going to get is some raw value coming out of the balance. And again, maybe it's not, you know, maybe the balance comes out with 102 and then maybe 0.5 and maybe negative 0.1. Again, I'm just making up these numbers, right? So all of this is test point 1. Maybe what we should do is let's add a subscript, or excuse me, a superscript 1 to both of these to denote that they're both test point 1. Right? Okay, so you go ahead and you store that data. Now you go ahead and do the same thing. Like, do it again. Apply test point 2. You know, maybe you continue with this pure lift, but you increase the magnitude, right? So now you have xbu 2 is, instead of 100 newtons, maybe you apply 150 newtons and 0, 0, right? This is what you apply to the balance. And then similarly, x raw 2 is going to be, I don't know, I'm making up these numbers, 160.2, negative 3, 4.8, you know, again, they're not reasonable numbers, but I'm just making it up. You get the idea, right? Then you could keep doing this. Apply test point 3. Maybe you move on to drag. Test point 4, you get side force. And maybe you do negative magnitudes, right? You probably want to cover and exercise a lot of the range of the balance, right? So you might generate n data points, right? Or n test points, right? So what you could do is, let's rewrite this equation for all of these test points, right? So for test point 1, you could write this as basically what? It's A xr1 minus xbu1 has got to equal 0, right? So this is basically test point 1, right? And then similarly, test point 2, it looks really darn similar, right? Just with 2's everywhere, right? I guess I should, right? And you do this, yada, yada, yada. You keep going until all the way to axrn, right? Minus xbu n, right? It's got to equal to 0, right? So this is test point n, right? Okay, so now what we could do is let's collect all of the known quantities in a vector, right? So let's go ahead and collect known quantities in a vector. Okay, let's call this vector maybe just x. So I'm going to stack these up, and let's grab all of the stuff we know in here. So that is going to be x raw 1, and then I also know xbu1, right? So I'm just going to stack those up like such. Then here, same thing, xr and xbu2, right? So here's xr2, xbu2, right? And then again, you keep stacking this all the way up until you get to x raw n, xbun, right? So this is a big giant fat vector of known values, right? Okay, so now what we could actually do is I can rewrite these equations, right? All of these equations, if you think about this long enough, this right here is 3 equations, right? Because again, this is a 3-element vector, right? So here's 3 equations, here's another 3 equations, all the way down to here's 3 equations. Okay? So I think everyone, if you stare at this long enough, you can see that I can rewrite all of these 3 times n. So all over, this is 3n equations. Right? I can rewrite all of those in matrix form, and that's going to look something like, well, here, maybe we should, let's do it over here. Maybe this is a little bit easier. Boy, this is going to be kind of big, but I think we can get by, right? So this is going to look like this thing, and I'm going to put this x here. Right, that's this thing, is going to equal a whole bunch of zeros, right? So this is actually going to be 3n elements, right? Because again, there's just 3n zeros all along the right hand side. So this matrix right here, if you stare at this thing long enough, you see that basically you get what? You get the A matrix here, and then you get a negative identity matrix over here. Right? So again, maybe I should write this like such. Okay? And then there's a whole bunch of zeros everywhere else. Dot, 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 0, 0. Right? Good. I think if you stare at this long enough, you'll see that this is indeed getting you this set of 3 equations, right? Okay, and then for this set of 3 equations, you see that this pattern kind of just moves. So you get the A and the negative identity matrix sliding over one spot, and then zeros everywhere else. So again, I think you'll agree that these 3 rows are equivalent to these 3 equations, okay? And I think everyone sees the pattern at this point, right? You just repeat this, right? And then until you get zeros all the way to A and then negative I, right? Okay, so this matrix, let's call this thing like, I don't know, maybe A tilde, right? And if you stare at this thing long enough, you see that, okay, this matrix, it has a pretty much almost like this block diagonal structure, and really there are only 9 unknown values in here, right? Because the only thing we don't know in this thing is the entries of the A matrix, right? And all of these built up together make this A tilde. So if you look at this thing long enough, we basically collapse all of these 3n equations into a single matrix equation, which looks like this, right? It looks like A tilde x is equal to 0, right? And again, keep in mind this is 3 times n elements, right? So you stare at this thing long enough and you say, okay, I know what this is, right? So this is known. We obviously know what this 0 is here, right? So the only thing we're looking for or searching for is basically this thing right here. We need to find or choose this, right? And this is basically how many free variables are in A tilde. We just talked about this, right? There are 9 free variables, right? Now, this is where this becomes a little bit of an issue, right? There are 9 unknowns, but you have 3 times n equations, right? So it's very possible that you have a over-defined system, and very likely you're not going to be able to solve this thing exactly, right? Because there's probably going to be no solution to this thing, right? But what you can do is, if you stare at this long enough, you see that this is actually interesting in the sense that the left-hand side, it's really it's effectively a vector, right? It's a matrix times a vector, which you kind of get as a vector, right? So you could formulate this entire thing as a optimization problem. Namely, if you go ahead and say, all right, why don't I solve this as a problem of, I want an objective function of, basically, I want to look at that the length of this vector, this a tilde times x, right? If I want to look at the norm of this, right? Would everyone agree that the thing inside the norm operation, this is nothing more than a vector, right? It's actually this whole thing together, maybe let's write it like this. This bit in here, this is nothing more than 3 times n element vector, right? Would everyone agree? And the idea now is you want to choose the elements of a tilde to make this vector, we need it to be 0, right? That's what it's supposed to be. So really what I'm doing with this norm operator is we're effectively making a cost function, which is going to penalize this. If you choose an a tilde, which makes this vector not near 0, it's going to have a non-zero length, right? It's going to have a non-trivial length. So that's bad. You want to pick a tilde to make the length of this 3 times n element vector as small as possible, right? So this is an excellent objective function. So you can basically say, one way to do this is, I want to now go ahead and minimize this objective function over all of the possible values of, the only thing we're actually changing here is a, right? Because a is what's baked into a tilde. So this is within our 3 by 3, right? So again, all you're doing is you're messing with the 9 elements of the A matrix, which in turn change the A tilde matrix, which in turn will go ahead and influence the length or the norm of this vector. And all you're trying to do is go ahead and choose the 9 elements, which make that as small as possible, right? So this right here is actually one way you can go about doing this. And another way to make the optimization a little bit easier is not going to change the solution, is you could go ahead and do your standard 1/2 in front, right? That does absolutely nothing for changing the solution. And similarly, since this norm here is always positive, I can square this without any kind of consequence, right? So this is one other way, or is sort of method number 1. We've formulated this whole problem now of picking the A matrix to make our data match as closely as possible of what was actually applied. That's basically what this optimization problem says, right? And there are plenty of optimization routines or packages where you can throw this now nicely well-formed, well-posed optimization problem at it, and it will go ahead and find you the optimal value of A, of these 9 elements of A, which go ahead and make this as small as possible. And again, what you're hoping is going to come out of this is that this A is going to look pretty darn close to the identity matrix with maybe some non-zero off diagonals, right? Okay, so that's the first way to go about this. That's method 1. Give me a second to erase the board, and let's look at another way to go about looking at this same problem. All right, so now on to method 2. So at this point, I think many people have probably thought about this in their head and said, you know, this is a pretty standard regression problem, and I don't disagree with you. In fact, why don't we formulate it as such? So again, what we can do is, here was our original equations for our first order correction, right? And again, these were 3 equations, right? So let's actually write this out in a more standard regression format. So tell you what, let's write out these 3 equations. So again, if you think about this, right, on the left hand side we had lift BU, drag BU, and side force BU, right, is equal to this 3 by 3 A matrix times XR, right? And in fact, tell you what, let's write this out instead of as a vector, let's write it out as the 3 equations. So this lift, drag, side force. So lift BU, I think it's going to be like that A matrix, it's going to be, there's like an A11, right? This is going to be multiplied, it's going to pick up the lift raw term, right? Plus an A12 drag raw plus an A13 side force raw, right? And then this one is going to be A21 lift raw plus A22 drag raw plus A23 side force raw, right? And then this is going to be finally A31 lift raw plus A32 drag raw plus A33 side force raw, right? So here are our three equations, right? And you can now clearly see the 9 unknowns, right? Were the 9 elements of that A matrix, right? Okay, so alternatively, you know, why don't we do this? We know we have all of the BU terms and the raw terms. The things we don't know are all these A's. So let's pull out all of the A's on one side of this. So in other words, what I want to do is, let's see if we can write this thing as, basically this left side looks like XBU, right? That's what all these 3 elements were if we stack them on top of each other. And then this is equal to basically this matrix. It's a 3 by 9 matrix. And then what I'm going to do is I'm going to stack up all of the unknowns here. So A11, A12, A13, A21, all the way down to A33, right? These are all of my unknowns. And I think, again, if you just look at the matrix equation, you're basically going to see that this turns out to be lift raw, drag raw, side force raw, and then 6 zeros. 1, 2, 3, 4, 5, 6, right? And then this next row is going to be 0, 0, 0, then lift raw, drag raw, side force raw, and then 0, 0, 0, and then 0, 0, 0, 0, 0, 0, and then lift raw, drag raw, side force raw, right? So this, let's call this matrix, how about B, right? And you can see that it is a 3 by 9 matrix, and all it does is it basically captures yeah, all of these terms, right? Okay, so all of the raw values that the balancer reporting are captured in this B matrix, okay? So here you go. This here, if you stare at this thing long enough, we can basically write this again now as just XBU is equal to B times, let's call this thing A bar. This is the vector of unknowns, right? So this is the thing we're solving for, right? Now, again, this is for one test point. So again, what you could do is let's add the superscript to the BU terms, right? These are the things that you apply to the balance, and then all of the balance measurements are captured in this B matrix. So we better have a superscript 1 here for the B, right? Because this is all for, this is here for test point 1, right? And again, you can do this for test point 2. So now you have XBU 2 is equal to this B2 and then times A, right? So here's test point 2, right? And again, you do this all the way down to your nth test point, right, is equal to BNA, right? And again, the thing that's nice about this is A is the same in all of them, right? We're trying to choose the exact same A value, right? Now, again, if you stare at this long enough, why don't we call the entire left-hand side? So again, remember, this is effectively 3 times n equations, right? That's what we're doing. Okay, let's stack all of these up as a big giant vector. In fact, we can call all of these, let's call it maybe capital X, right? So I'm going to write this whole thing as these 3 n equations as a one big giant matrix equation as, let's call it capital XBU. Okay, and this is a vector, right, is equal to, and I'm going to stack all of these B's on top of each other. I'm going to call this maybe B tilde times A, right? So in this case, this capital XBU vector, right, it's nothing more than, again, all of the XBU terms stacked up on top of each other, right? Right, so again, this is nothing more than a 3 times n element vector, right? And now this B tilde matrix, it's nothing more than the B1 matrix, then you stack on the B2, and then all the way down to the Bn, right? So this thing is a 3 times n by 9 matrix, right? So you write this whole thing in this format, right? Now, if you stare at this thing long enough, this looks like, I mean, you look at that thing, doesn't that look a whole lot like, it looks similar to, you know, a B is equal to the AX, AX is equal to B, right? It's just vector equals matrix times vector. Vector equals matrix times vector, right? This is a well-known problem, right? Of if someone gives you the matrix A, someone gives you the matrix, the vector B, what is the X that is going to make these two things true, or at least as close to true as possible, right? Because again, we're still in an over-defined situation, right? There are 9 unknowns, right? So these are the 9 unknowns. But you have 3 times n equations. So again, it's over-defined, right? That's the whole point of regression, right? Is to find this vector so that the left-hand side is as equal to the right-hand side as possible, with the understanding that you're probably not going to be able to make them exactly equal. We need to find the A that's going to make this approximate, as small a discrepancy as possible. Right? So again, if you stare at this thing long enough and you realize that it's nothing more than an AX is equal to B problem, right? You can also set this up as an optimization problem where all we want to do is again, similarly, I want to minimize the difference between these vectors, right? This B tilde A, right? That's the right-hand side. I need to subtract this from capital X BU, right? That's the left-hand side. So I want to make the difference between these two things as small as possible. And if I do the same trick as last time and basically put a 1/2 and square this, again, I don't change the solution. All I do is I formulate this in a more standard optimization framework. And all we're doing here is minimizing this all over the possible values of this A vector, right? Which is a 9-element vector. So it's a 9-element real vector, right? So that's all you're doing, right? Is solving this optimization problem. And again, this turns out to basically be a very similar, I mean, it is this problem, right? Minimize AX minus B, right? And find the X that does that. So the solution to this formulation is actually the well-known pseudo-inverse, right? Pseudo-inverse. Right? So the solution to this is basically that the A, and let's put a star on this. This is the value of A that is going to make this problem optimal here. This thing is going to be the pseudo inverse of which is given by B tilde transpose times B tilde, right? Inverse times B tilde transpose times capital X BU. Right? So again, this is awesome, right? Because again, stare at what we know and what we don't know. We know what B tilde is, right? B tilde is just this matrix here where you have basically stacked up all of the raw measurements that the balance has reported for all of the different test points, right? And then what else do we know? Oh, well here, capital X BU. Right? That is nothing more than all of the actual known forces and moments or whatnot that you actually applied to the system, right? And you stack them up in this vector. And this is your pseudo-inverse closed form solution, which will tell you the A matrix, or excuse me, the A vector, which really is nothing more than this A matrix that we were originally looking for, right? So here you go, in one page on the board, this is one way that you can go about finding a optimal set of balance interaction equations for this first order system, right? And now you see why we, at the beginning, we wanted to work with this simpler 3-force balance, right? Rather than 3 forces and 3 moments, and why we also wanted to deal with just a first order correction instead of a second order correction, but the idea is the same. Right? So now if you want to scale this up to a full 6-component balance with a second order correction, you can basically do something similar to this, and off to the races you'll be. Okay, so I think that covers correction number 2, which was our balance interactions. Let's move on to correction 3. All right, so the third correction that we might want to account for is basically different types of aerodynamic tears. So this is both tears for effects due to this strut or fork that is mounting the model and connected down to the balance, as well as for interference that might be caused by this fairing, right? So again, just to refresh your memory, obviously this is the desired configuration of what we want to simulate, right, in the wind tunnel. So we want basically just the aircraft, and we just want the aero effects. You know, this is the aero forces and moments, right? The aerodynamic forces and moments just on the aircraft, right? Now, here's what we're actually testing in the wind tunnel, right? You've got this model in the wind tunnel, and now, like we said, this strut or fork, right, is what's attached to the model, and it basically goes down through the fairing all the way down through the balance, right? But it has this exposed section which is exposed to the air. So any drag that is incurred by this strut, or any forces or moments that are incurred by this strut, are effectively mixed in with the aerodynamic forces and moments that are applied to the model. So it's like the balance doesn't know, the balance is going to think that this is an aircraft with a big fat ugly landing gear basically hanging out in the wind, right? Because any aerodynamic effects on the strut are going to be transmitted down to the balance, right? So that's one problem here, is that not only in this configuration, right, we do get the aero effects, right, but we also have strut, whoops, I spelled that wrong, S-T-R-U-T, strut effects, right? That's also present here. It's like because we've got this part here connected to the aircraft. Also, since this is subsonic flow, and actually we've got flow coming around this fairing, right? So this fairing right here is not connected to the balance. So any forces and moments that are ripping or pulling or pushing on this fairing are not going to be read by the balance, because this is not connected to the balance, right? But it is going to deflect the airstream, right? It's going to interfere with the flow underneath the model, right? So we also have that effect present. So there's strut effects, and also there's interference on the bottom, right? So all of these three effects are going to be amalgamated together and measured by the balance, right? So that's one problem here, is that in the wind tunnel, right, we've got this test configuration, which includes the thing we want, plus some of these strut effects, plus this interference on the bottom of the aircraft, right? So the question now is there some way we can tear out this bit and this bit, right? These are two things we don't want, thereby recovering just the aerodynamic effects, right? So that's the game plan. How can we go about doing this? So what we're gonna do is, let's go ahead and run a series of different tests. So let's call this maybe run A. So this is the upright configuration. So let's call this run A. This is upright. Okay? And, sorry, excuse me, I labeled that wrong. This is what we want. We can't do run A. This is run A, sorry. Run A. This is upright. Okay? So we do this, okay? Now what we're gonna do is let's go ahead and make a run B, okay? So the way run B is going to work is, again, you still got the fairing right here, and you've got the strut, but now what we're gonna do is let's invert the model. So instead of having it sitting like this, let's literally flip the thing upside down. And again, I apologize, I'm not the best artist. Hopefully you see what I'm trying to get at. Close enough, right? So this run B is inverted, okay? And what you're gonna do is we're gonna run the same kind of conditions, the same angles of attack, the same dynamic pressure, all that kind of good stuff. So what should the balance measure in this configuration? Well, again, if you think about this long enough, since from an aerodynamic perspective, it doesn't matter if it's upright or upside down, right? The airflow is still coming at it pretty much straight on. So in this case, we still have aero effects, right, present. And look, there's still this strut. In fact, it's pretty much the exact same amount of strut is exposed in both of these cases. So I think you would still agree that you also have strut effects. The same strut effects are present in this run. Now, what's interesting though is the interference is actually going to be coming from, and it's going to interfere with the top of the model, right? So now you have interference, right, on top of model. Maybe we should have written it on bottom of model in these cases, right? Does that make sense? Okay, and also while we're at this, let's go ahead and do a run C, which is going to be inverted plus what we're going to call the image fairing. Okay, so what this run C looks like is, again, we're going to keep the model inverted, right? While we've already got this thing turned upside down, let's see how much of this we can, how many birds with one stone we can kill, right? So you've got this thing inverted, but now what we're also going to do is we're going to insert from the ceiling of the wind tunnel a image fairing, right? The idea with this image fairing is that it is a mirror image of the fairing that's down here on the bottom. So again, let's make a note here that this is what's referred to as non-metric, meaning it does not touch the balance, right? So that's great. While we're at this, let's also mount another secondary image strut as well, which is metric. So we're going to put a image strut, which again is just the mirror image strut of this other one, and this one is metric. So again, this strut is attached to the model, which is attached to this strut, which is attached to the balance. So we're going to measure the effects of this strut here. So it's really, it's almost like a mirror image setup on the top, okay? Or on the top of the wind tunnel, which is really the bottom of this inverted model, right? Now, let's think about what are we going to capture here? What is the balance going to be reading in this situation? Well, again, you're going to get arrow effects, right? We're going to get strut effects from this bottom one. So let me write this down one time. So strut effects, right? We are now also still going to get interference on the top of model, right? And now, due to the fact that we have this whole image strut and fairing setup up here, we're also going to get strut effects again, right? These are the strut effects due to this metric image strut that we put. And we'll also get still interference, right, on the bottom of the model now, right, from this image fairing that we've got up on the top, right? Okay, great. So now that we've done these three runs, run A, B, and C for the same configuration, let's go ahead and see what happens if we were to go ahead and take run C minus B. So literally take this, this run, whatever forces and moments are measured during run C, subtract whatever forces and moments are measured during run B. What are you going to get? If you look at this long enough, right, what do we have during C? C, we have arrow effects. Well, you know, maybe we should write this. Well, I think you can kind of see it right here, right? See, this arrow effect will be canceled by this. So this will be gone, right? Okay, and then you've got strut effects here from this strut, right? From the bottom strut, that's going to be canceled by this. Then we also have interference on the top of the model, which will be canceled by this. So what will be left over with is the difference between C and B is going to basically just hopefully have left strut effects and then interference on the bottom. Okay, so I don't know, why don't you call this like run D or something like that, right? And if you look at this long enough, right, this is exactly what we're trying to remove from run A, right? We want to get rid of the strut effects as well as the interference on the bottom. So this is sometimes referred to as your S&I, or strut and interference tare. And I guess technically, to be true, what's done at the tunnel and what you should probably do is you get this value D here, and you may want to probably normalize it by the dynamic pressure at which it was acquired. Therefore, you're going to have a strut and interference tare that you can apply to different dynamic pressures as well, because you don't want to have to do this for tons of different dynamic pressures, right? So you might want to just do this for a nominal dynamic pressure and then normalize it by the dynamic pressure. So really, to be a little bit more accurate, you know, what you may typically see in some tunnels is that the T and I interference tare, let's call it T, it's really this D run normalized by the actual dynamic pressure here, right? So this is the strut and interference tare, which is normalized by QA, by dynamic pressure, right? Therefore, this tare here can be applied to other situations which have maybe different dynamic pressures. Right? So, yeah, so as you can see, once you generate this tare T, all you need to do now is basically take whatever data you get at a normal standard upright configuration and then just subtract out T and multiply by QA, right? So in other words, what we want is maybe, let's just do it for one channel, like for example, lift that is now corrected for tare and interference, right? As well, this is going to be lift BU, right? So again, lift BU is what we talked about in correction number 2. This is the lift that has now been corrected for balance interactions, right? But this thing still has the effects due to the strut and due to the interference on the bottom, right? So now what we're going to do is we're going to correct it by subtracting off that tare. So now we're going to subtract off that tare value of lift, right? But then we're going to have to multiply it by the dynamic pressure of this particular run, right? So great, and you can do this for all the other 5 channels as well, and this gives you basically a way to correct for the strut effects plus the interference on the bottom of the model, right? So this is kind of interesting, but you know, in the interest of full disclosure, I will say I think this is probably a little bit of an outdated method and testing methodology. I mean, you will see it done. In fact, you know, here's a picture of it actually being implemented at the Kirsten wind tunnel. I believe this is on a 757 model, so this is done. But if you think about this long enough, it's the reason maybe it's fallen out of favor is that in addition to you're doing your normal upright run, you also have to do an inverted run, and you have to do an inverted run plus an image fairing. So it's time consuming, right? Instead of doing 1 run, you're now doing 3 runs, and you don't want to do this for every single configuration. So it might be a situation where you develop a tare for like maybe your baseline configuration, and then just apply that for other configurations as well. You know it's not going to be exactly correct, but it's better than nothing, and it's going to save you the time and money of running all these extra runs. And then also, you know, in addition to running the extra runs, you got to build a model which is able to accommodate being inverted as well as having an image fairing installed. So you got to do some of this pre-planning ahead of time before you get into the wind tunnel. It's not one of these things you can just drop in and say, oh, hey, you know what? Maybe it is a good idea to do tare and interference. Let's go ahead and run those tests. Well, if you didn't plan your model for that, you're not going to be able to do that. So something to think about. Okay. Let's move on to correction number 4, which also is another type of tare, actually. All right, so on to correction number 4, which is applying weight tares. So the idea with a weight tare is, again, we go to the wind tunnel to get the force and moment, the aerodynamic force and moment data, right, acting on the model. Now, what's interesting is you got to remember the wind tunnel, right, is going to measure the moments, namely the pitching and the rolling and the yawing moments about a specific location, which we talked about earlier is referred to as the balance moment center. I'm going to draw it like this. So this is the balance moment center, okay? Now, what's interesting about this, right, is often the balance moment center does not align with the center of gravity of this wind tunnel model, right? So the CG of the wind tunnel model, let's go ahead and write it like, you know, I'll draw you like your typical CG diagram, right? So here's the center of gravity of the model, right? Because again, you got to remember, this model is made out of, you know, solid aluminum or whatnot, and it's got some weight distribution. So its center of gravity is out here, right? Now, the fact that the center of gravity is not located at the balance moment center means that even if the wind is off, right, the weight of this model is going to pull down like this. And you can see right here that the weight of the CG not being at the balance moment center means that the balance is going to measure a pitching moment even though the wind is off, right? Even though there's 0 possibility for aerodynamic moments to be applied to the model, the balance is going to say, oh, I measure some amount of pitching moment. You know, for example, I've got, I can demonstrate that right now, right? Let's pretend this is my wind tunnel model, right? And I am the balance, right? And I'm going to measure forces and moments around, let's pretend my hand is the balance moment center, right? So if I if I mount the model like this and I close my eyes, I don't even know if the wind is on or what the orientation of the model is, right? But right now, when I close my eyes, I can tell my hand, I feel some pitching moment. I feel some nose down pitching moment. How am I supposed to know if that nose down pitching moment is due to actual aerodynamic forces and aerodynamic moments on the model, or the fact that the center of gravity is not where at my hand? And in fact, this gets exacerbated what if I yaw the model like something like this? Now I feel some rolling moment too, right? So now I'm measuring pitching moment and rolling moment just purely due to the fact that the center of gravity is not at the balance moment center, right? Does that make sense? So we just need to tear out this effect. Right? So that's literally all we need to do, is we need to account for the fact that even when the wind is off, there is a pitching moment and a rolling moment due to the center of gravity being at a different location, right? Okay, so in order to correct for this, there's actually two very common ways to apply this weight tear. So method one is sometimes referred to as a full table tear. And this is actually really simple, okay? So the idea is with the wind off, right? So step one is wind is off. Right? So with the wind off, we can pretty much guarantee that there are zero aerodynamic moments acting on the model. Any moments that the balance experience is purely due to this effect that we're talking about, that the center of gravity of the model is not at the balance moment center, okay? So with the wind is off, the next step is all you want to do is basically pitch and yaw to a location, right, to some angle of attack, some angle of yaw, and 3, then you just take data, right? Whoops. 3, take data, right? And then 4, just go ahead and repeat at different alpha and psi, right? Different angle of attack and different yaw angles, right? So you're basically, if you repeat this for every single angle of attack and every single angle of side slip that you expect, you will basically go ahead and build up a table of what is the rolling moment and pitching moment due to the center of gravity at all of these different conditions. And you know, maybe what we should say here is when you're taking data, all you really care about is the rolling moment and the pitching moment. You really don't care about yawing moment, because if you think about this long enough, right, the fact that the CG, the fact that gravity acts in the perfectly downward direction means that you actually don't get a yawing moment due to the center of gravity being offset, right? Okay, so this is what's known as a full table tear, right? Okay, that's method 1. Method 2 is referred to as a 3-point tear. Right? So again, the procedure for this is, again, the wind is off, right? Okay, and what you're going to want to do is you're going to want to take data at some point. Usually the most common is at alpha and psi is equal to 0, right? And then next what you're going to do is you're going to take data at another second point. Again, the most common one is a positive alpha and a most positive psi. So yaw, pitch the model up far and yaw it out to another location, right? And finally, step 4 here is, again, take data at a third point, which is basically negative alpha and negative psi is a very common one. Now, interestingly, you don't need to take it all, this last one, but it's good for redundancy. And because if you think about this, what we need to know is you need 3 pieces of information, right? If we can find out the weight of the model, and then the X and the Z, or I guess technically X, Y, and Z. It's possible that your model doesn't have a, it's not symmetric here. So you have the X CG, the Y CG, and then the Z CG. Okay, so here there's actually 4 unknowns. Okay, so when you take data here when the wind is off, this almost gives you enough information to get the weight. This is almost like equation 1, right? And then here's like equation 2 and equation 3 and then equation 4. So with these 4 pieces of information, 4 equations and 4 unknowns, you can basically solve for what is the weight and where's the position of the CG need to be in order to get consistent data with these 4 data points that you collected, right? So again, it's very similar to the balance interaction discussion, where this is just a regression problem at that point, right? So what you can do is you can obtain these 4 pieces of information, and then you can forward calculate for any other arbitrary angle of attack and angle of yaw. You can basically calculate what should the rolling moment and the pitching moment do to this offset CG be, right? So with this information, you basically generate almost effectively the same information that you get from the full table tare. So again, there's multiple ways to go about this. Usually this 3-point tare is much more common because, as you can see, it's much faster, right? You basically take, you take a wind off 0 right here. You take 3 other data points and you're done. Whereas here, you need to take the wind off 0 and then you need to take a whole bunch of other data points at a whole bunch of different conditions. So again, this is much more popular because it is basically faster, right? Okay, but either way, long story short, at the end of the day, either one of these techniques are going to give you an idea of how to basically estimate what is the pitching moment and the rolling moment weight tare. So this whole idea with a weight tare, right, is that you need to basically be able to feed it the angle of attack and the angle of side slip of the model. What this will spit out for you is the pitching moment that needs to be removed and the rolling moment that needs to be removed due to the weight tare. And what we're going to do is we're going to apply this to our data. So remember, we had the pitching moment, which was now corrected for tears and interference, balance interactions, QA to QI, all our previous discussions here, right? But now we also have to subtract off the pitching moment due to the weight tare, right? And this will give you basically the pitching moment. Let's call this thing B. Again, I'm just using subscripts. So this again is now, this is corrected for everything we've talked about, steps A, B, C, D, right? And this is corrected A, B, C, right? So everyone gets the picture here. So again, it's similarly, rolling moment B is just going to be rolling moment that we corrected for previously minus the rolling moment due to the weight tare, okay? And again, like we said, there's no yawing moment due to the weight tare, so we don't need to correct it. So I guess if you want to keep a set of consistent subscripts, so the yawing moment B, it's just yawing moment TI, right? The yawing moment that we corrected for tears and interference and everything else previously, right? Okay, so that allows us to take into account the fact that the CG of the model is not at the balance moment center. But now let's go on to our 5th correction, which is again also related to center of gravity, but now we're going to be talking about the center of gravity of the real or the projected or the designed aircraft, not of the model. All right, so now on to step E, which is the idea of moment transfer. So this is the same picture we had when we were talking about weight tares, and I wanted to keep it up because it's actually very relevant to our discussion of moment transfer. So again, just to refresh your memory, right, this was our picture where we talked about the wind tunnel, right? Now that we've made all these corrections, it's actually measuring the moment, it's the aerodynamic moment. I'm going to draw it as some arbitrary vector, right? This is the aerodynamic moment about the balance moment center, right? That's what it's measuring and reporting. It's reporting moments about here, right? So let me take off this weight vector, right? I just want to just show that, okay, so this was again the CG of the model, right, that you've got sitting here in the tunnel. Okay, now we are able to correct it and basically get forces, or we're getting moments now that are measured about the balance moment center, right? But what's interesting about this is the balance moment center is probably not going to be the location that we care about. What we're ultimately wanting to do is we will ultimately want the aerodynamic data to represent the actual aircraft, which might have its center of gravity somewhere else. Like, you know, for example, I'm gonna draw it as a green center of gravity symbol, right? So this is actually the projected / estimated slash desired, however you want to think about this, center of gravity of the real aircraft, right? So what I actually want to do is I need to take the wind tunnel data, which is giving me the aerodynamic moment about the balance moment center, and instead I need to transform this into the aerodynamic moments about this location. This is typically referred to as the model moment center, or MMC, right? So MMC is, again, this thing, right? It's the model moment center. It's a projected or estimated or desired location of the real aircraft, right? That's where we want to transfer the moments, right? So really, we have to do pretty much your standard moment transfer set of equations where you have 3 forces and 3 moments. So to simplify this, let's just look at you know, a one-dimensional picture, and then we'll generalize that later to a more complicated scenario. So the picture that goes along this is really easy. Let's simplify our vehicle into just like maybe like a single bar, and let's look at 2 points, like point A and point B. Okay, now let's go ahead and look at maybe a really simple situation where this model only has a lift force associated with it and a pitching moment. Let's call this P. And now we got to specify this is a pitching moment about point A, right? Okay, so now what we would like to do is we would like to look at, can I transfer this moment, right? So instead of pretending that I care about moments about point A, what if we want to transfer it over here to point B? So the force, right, there's no such thing as a force transfer equation, right? It's just moment transfers. The moment, it depends on which location you take this moment about, right? So here I would like to now transfer this moment over here, so you have pitching moment B, right? And I want both of these pictures to be equivalent, right? So this is actually pretty darn simple. All you need to do here is look at this first picture, right? In this situation, let's go ahead and write an equation for the moment about point A, right? Okay, so the moment about this, since this lift force acts exactly through this point A, it doesn't have a moment arm, so it doesn't contribute. So the only pitching moment we have about here in this picture is just PA, right? Okay, now let's do the same thing down here. I want, in this picture, I want the moment about point A, right? So in this case, the moment about this location, it's, there's this couple PB, right? So there's PB, right? But now I also have to take into account the fact that this force lift acts at a distance away from point A. So now I have to define a moment arm. So I'm going to define this as being positive S. Right, that's my distance S. And again, this is maybe, we should maybe be a little bit careful and denote that a positive pitching moment implies counterclockwise rotation in this scenario. Depending on your wind tunnel or depending on your application, you just got to make sure you keep the signs appropriate. So now what we have to ask ourselves again is here, okay, pitching moment about this point A. So does this lift force at a positive S, does that create a positive or a negative pitching moment? So in this case, we see that actually this positive lift force at a positive S tends to produce a clockwise rotation, which is actually negative, right, in our sign convention. So I need to go minus S times L, right? Would everyone agree? Great, so now I just need to equate this to this, right? Because both of these expressions tell me the moment about point A. So basically what we have is the pitching moment A is equal to the pitching moment B minus SL. Right? So this is effectively a moment transfer equation where if you have a situation where the balance is reporting moments about point A, and you want to transfer it to the moments about point B, you can basically use this equation to solve for that, right? So you would just move this to the other side, right? So again, this is in one dimension. Now where this gets interesting is, what if there are, there's also a drag and there's also a side force, going into or out of the board? What if you have different moments? What if you have different moment arms as well? So again, you can expand this to multiple dimensions, but this is the concept of a moment transfer, right? In a very simple case. So I'm going to leave the exercise of the full three-dimensional moment transfers with 3 forces and 3 distances. I'll leave that as an exercise to the reader in the homework. But again, this is the idea with the moment transfers. Again, at a very high level, all we're doing now is through these moment transfer equations, we are basically going to take the aerodynamic moment that is measured by the balance about the balance moment center, and we can now transform that into an aerodynamic moment about some specified model moment center, right? And again, we care about this because this is the aerodynamic forces and moments that are going to actually act on the real aircraft when it has its CG at this model moment center. All right, so now we're on to our 6th correction, which is a blockage correction, which we're going to see is actually, it's another dynamic pressure correction. So remember, all the way back in step 1, what we did was the very first correction was we said we were going to measure the dynamic pressure in the empty test section via the static pressure strips that were on the floor and the ceiling of both the test section and the bell mouth, right? And what we did was we corrected the indicated dynamic pressure to the actual dynamic pressure using that fudge factor of QA over QI, right? So the thing we got to keep in mind is that QA was using the empty test section. So the empty test section had I think we called it a cross-sectional area. The terminology we used earlier was A2, right? Because A1 was the cross-sectional area of the bell mouth. A2 was a cross-sectional area of the empty test section. So by the time the air contracts from A1 to A2, right, it accelerates, all that kind of good stuff, right? And we basically have the dynamic pressure in the empty test section, right? Due to that contraction, right? That's what the bell mouth did. Okay, one thing I want to do is let's switch our notation for this. A2 is sometimes you'll see in tunnel documentation referred to as CA, or the cross-sectional area of the empty test section. Okay, so that's this term A2. Now remember that thing that we obtained in step 1, right? In step 1 we obtained QA, right? That was what we call the quote-unquote the actual dynamic pressure inside this empty test section, right? Now, here's the rub, right? This might be accurate, but it's accurate for an empty test section. We're not testing something with an empty test section, right? What we're doing is we're jamming a model, we're jamming a fairing, a strut, a model in here, right? So if you notice, and think about this, all this is sometimes referred to as quote-unquote blockage, right? In the sense that we've reduced the cross-sectional area of the test section, right? So in this case, this area is less than CA, right? Because you've got this model blocking. It's effectively like sticking your thumb a little bit over the nozzle of a garden hose, right? You're increasing the velocity at the model, and therefore you're increasing the dynamic pressure at the model. So this dynamic pressure, the dynamic pressure Q is probably greater than QA. Wouldn't you agree? Right? Compare these two pictures. And here's where it gets even more interesting, right? Let's say this, I've drawn a picture here at an angle of attack of about 0 and an angle of side slip of about 0, right? So the aircraft is aligned with the flow. It's probably as most efficient as possible. What happens if you yaw the model out and pitch the model? So I've drawn an exaggerated diagram here where the model is, pitched up, yawed out, and again, as you can see, the blockage problem gets even worse, right? Because the cross-sectional area of this picture is even less than the cross-sectional area of this picture. So again, you've stuck your thumb even further over the hose of the garden, over the nozzle of the garden hose. So the dynamic pressure here is even more greatly increased, right? Because here the area is let's use this notation, much less than CA, right? So now the actual dynamic pressure is much greater than QA. And again, the much is again it's not really a ton, we're talking a couple of percentage, but it's a non-trivial amount, right? So the thing to think about this with this is that when you stick a model in here, you are blocking the tunnel, right? You're reducing the cross-sectional area of the test section, and that blockage is not static. It's a function of the attitude of the aircraft. And if you think about this even more, right, this model is probably producing some wake, right? In fact, if you watched our first video, right, of this wind tunnel series, right, I talked about, we actually did some testing where we were surveying the wake of the model, and the effects of having this model in here, it actually slows the momentum of the flow, not just directly behind the model, but it kind of increases, right? The wake, as it moves downstream, it kind of grows. So you're almost, that's almost like blockage as well, right? You have this area of reduced momentum, which, you know, all these effects together serve to effectively decrease the cross-sectional area of the tunnel, thereby increasing the dynamic pressure at the model, right? So this is what we've got to account for, and this is what we've got to correct for. So the correction that is typically done is we're going to now say, I need to take the dynamic pressure and I need to correct it. So we need to get this, QC. So QC is going to end up being, the way we do this in the Kirsten wind tunnel is, we're going to say that is the actual Q, right? Which again we got was corrected from the indicated Q. This was what we got out of step 1, right? But now we need to correct it for all of this effect of having the blockage of the model, having the blockage of the wake, all that kind of stuff, right? So this is going to be 1 plus epsilon squared. And in this case, this epsilon is basically it's like a blockage correction factor, right? And it is typically something small, right? You can see if epsilon is 0, then this goes away and we basically have no effect of blockage, right? But if epsilon is some small number, it will increase and it will change the dynamic pressure in one direction or the other. Either goes up or goes down. Typically, right, the dynamic pressure is going to go up, right? So this is typically a small positive number, right? Okay, so there's 2 methods to go about calculating this epsilon factor, right? And there's the 2 ways that we do this is method 1 is referred to as Shindo's simplified correction. Okay, so in fact, this was a technique developed by Luke Shindo, who actually was a University of Washington Kirsten wind tunnel employee for quite a long time. He was very influential in developing the testing procedures at the Kirsten wind tunnel. He's published several papers. He's kind of a legendary figure around the University of Washington wind tunnel. In fact, here's one of the papers that he developed and published in the Journal of Aircraft, which describes this technique. So if you're more interested in this technique, feel free to check out this reference. I'm just going to give you the nitty-gritty, write down the equations that are applied and provide a little bit of exposition on them. So in this method 1, he says epsilon here can be calculated as such. So it's the wing area of the vehicle all over the cross-sectional area of the empty test section times the quantity CDU minus CLU squared times 1 over pi AR minus SW CW all over CA. Okay, so in all of these terms, you know, basically you just plug this in and you should get a small positive epsilon number out of this. And again, I don't fully understand this. Don't quote me on all of these quantities, but again, you know, SW is I believe the wing area. We already talked about what CA was, right? CA is the area of the test section. I think this is with fillets. I can't remember exactly. Remember, the fillets were these corner sections of the test section here. I think CW is maybe the area of the test section without fillets. You know, obviously we know what AR is, right? AR is the aspect ratio of the vehicle or of the aircraft. The CDU and the CLU, these I believe are uncorrected drag and lift, respectively. Okay. And again, I don't think we want to you know, go into this. In fact, you know, Luke talks about these in his paper, so feel free to check that out. But if you look at this, you can see it's got the bones of being something reasonable, right? You see that as the cross-sectional area of the test section increases, right? This factor starts decreasing, right? Which again makes sense. If the test section is giant compared to the model, right? This blockage correction is not going to matter as much, right? If you have an enormous wind tunnel and a tiny little model, there's probably not going to be any effect due to blockage, right? Conversely, right? You see SW is in the numerator, right? So if you have a giant model with a huge wing, right, that has the potential to block the test section like significantly, this factor is going to go up, right? And similarly, you see here, you have the lift and the drag, right? Also kind of as numerator terms in the sense that as these things increase, right, so does this. Right? So again, this kind of captures the dynamic behavior of as you increase the lift or you increase the drag or you pitch and you yaw the model, right? These terms are going to start contributing. Right? So again, it's got the bones, I think, of something that's reasonable, and in fact, it's shown in this paper why this is a reasonable approach, and it turns out this is actually used quite extensively, and it's very popular as a technique to go about and apply blockage correction. So again, as you can see, at the end of the day, you turn the crank, you get some small positive number, you stick it into here, and you can see what the net effect is that your actual dynamic pressure at the model that is corrected for blockage and corrected for QA to QI, this is slightly higher than the QA that we calculated in step 1, right? Okay, so that's the first technique. Tell you what, give me a second to erase this and we'll talk about another way to get this epsilon factor. All right, so the second popular way to calculate this blockage correction is what's known as Pascal's blockage correction. And again, this epsilon term is now just the sum of two separate epsilons. So Pascal explicitly corrects for the blockage due to solid blockage, this subscript SB, as well as the wake blockage, which is this, again, subscript WB. So same thing with in a similar fashion what we talked about with Shindo's method here. I don't have the expertise to derive any of these. I'll refer you to some other references at the end of this video where you can look up more about this blockage correction factor. But again, if you just stare at the equations, we again see that it's got the rough behavior that we're interested in, meaning the solid blockage right here, these Ka, Va, Kb, Vb, these have to do with the volume or the size of the solid body here. And as you can see, that is in the numerator. So as your model gets bigger, the blockage correction due to solid bodies increases, and then you have the cross-sectional area of the test section in the denominator. So again, the way you can combat this problem is you can just get a larger test section, right? If the test section is bigger, these bodies of blockage, of solid blockage, are going to, its effect is going to be decreased, right? So you've got this due to solid blockage. Now, the wake blockage is what's interesting here. The wake blockage, has a similar flavor, right? The bigger the wing you have, the SW, the more wake this thing is going to produce, so the more blockage you're going to get. And again, we see the cross-sectional area of the test section is in the denominator like we expected. But then you see terms like CD not, CD uncorrected, CD induced, all this kind of stuff which has to do with moving the aircraft, right? So as the model has more drag, right? And drag is directly proportional to the size of the wake, right? Well, maybe not directly proportional, but proportional, right? It's related here. As you increase the amount of drag, you increase the wake blockage of the model, and therefore you increase this wake blockage factor here, right? So again, I'll refer to you to a book at the end of this video where you can look up more about Pascal's blockage correction. But again, it's got the bones, it's got the feel, it's got the general behavior that we're looking for. So again, it's just another way to calculate epsilon, which now allows us to correct the dynamic pressure at the model, which now takes into account the fact that the model and its wake are blocking the test section and therefore increasing the dynamic pressure at the model. Okay, I think that's a good discussion on blockage corrections. Let's go ahead and move on to the next one. All right, so at this point, I think we've done enough corrections that we're able to calculate some initial aerodynamic coefficients. So again, these are, we're going to use the subscript INI to denote that they're initial and distinguish those from the final corrections that might take a little bit of post-processing. All of these coefficients can be calculated sort of quote-unquote on the fly, in the sense as the test is progressing, we can basically calculate all of these and present them. The customer can look at them and understand, you know, are things looking okay, and they can make decisions kind of on the fly. But these are, again, our initial coefficients. They're not going to be the final ones. We're going to discuss some future steps in data reduction processes that are going to turn these initial coefficients into final coefficients. That being said, let's talk about the initial ones. So for example, your initial lift coefficient, it's just the lift. And again, remember, LB, this is the lift that is now corrected for everything we've talked about in steps A, B, C, D, E, and F, all right? So this is corrected for balance interactions. It's corrected for strut tears and interference, all that kind of good stuff. And then the dynamic pressure here, notice it's QC, right? It's the corrected dynamic pressure. So again, this is a pretty good approximation, or a good version of the lift coefficient. Same thing for the drag coefficient and the side force coefficient. The thing I maybe will call out is some tunnels and some texts use CY to denote side force. So again, just make sure that you're clear. This is not yawing moment, right? This is side force coefficient, right? So your force coefficients are pretty standard. Similarly, your moment coefficients on this side, there's a couple of things I'd like to draw your attention to. First off is this this XX additional notation. Remember when we talked about moment transfers? You can transfer the moment measured by the balance to any arbitrary location, right? So it's customary that sometimes a customer is going to want multiple different moment transfer locations. So they might want one here, you know, right at the leading edge of the wing. They might want one that's a quarter chord back, half chord back. Basically, they might want to be interested in understanding how the moment coefficients change as the virtual projected center of gravity of the vehicle changes, right? So for example, as fuel burns, right, the CG on the aircraft is going to change, so it's not going to be static throughout the flight. So they might want to see, how does the moment coefficients look as the CG moves? So a lot of times you'll see this XX notation to denote, are you talking about like which center of gravity or which model moment center are you referring to? So again, this should match up with whatever model moment center is being used here, right? So again, your moment coefficients, again, it's just your standard moment, aerodynamic moment coefficients, where you have the moment and it's normalized again by the dynamic pressure, a reference area, and then a reference length, okay? So the thing that I also want to maybe draw your attention to right now is, notice that for pitching moment at the Kirsten wind tunnel, we use the mean aerodynamic chord as the reference length for pitch. But for roll and yawing moment, notice here that the reference coefficient is actually now a reference span. Or yeah, the reference length is some reference span, like the wingspan or half of the wingspan. The customer can kind of pick that. I just want to point that out, that they are different, right? This pitching moment coefficient is different than the rolling or the yawing moment coefficient. Again, I can't stress that enough. Keep that in mind, because this is going to come back later on down the road when we're talking about axis transformation. So I just wanted to explicitly draw your attention to it right now, that they are different, okay? And as long as we keep that in the back of our head and we remember it and we do our accounting properly later on, this won't be a problem. But again, I just want to stress that and bring it to your attention here. Okay, so I think that is a pretty good discussion on the initial coefficients. Let's go ahead and move on to additional, now sort of more complicated corrections that might need to be done after the test is completed. All right, so let's keep going. Our next correction is actually a really interesting one, and this is correcting for what's known as flow angularity, also sometimes referred to as an upflow or a crossflow correction. So the idea with this correction here is, let's take a look here at our wind tunnel setup, right? So here's a side view of the test section, right? And I've drawn here in blue the X axis going straight back of the tunnel, which is, you know, parallel to the floor. The y-axis, which is also kind of parallel to the floor, but coming out the kind of from the center of the test station out towards through the right wingtip of the vehicle. Well, I shouldn't say that. It's not toward the right wingtip of the vehicle, right? Because the vehicle can be pitched or yawed. It's basically just coming out. And then the z-axis is from the balance moment center of the origin, pointing straight up, so normal to the surface of the floor, going straight up towards the ceiling, right? Now, what's interesting about this is, again, the balance, right, or the wind tunnel, it's going to report to us. Let's just take a look at the forces to start with, right? So the aerodynamic forces, right, it's going to be giving us, let's just say, you know, what is the force in the x-axis, right? It's in this direction, right? Now, the tunnel is going to report this as drag, right? This looks like drag to me, right? So what you're going to get here is, you know, we have been calling this term basically, you know, CDINI, right? That's your initial drag times QC times SW, right? Would everyone agree that this is the force that is aligned in this blue X direction, right? Now, what's the force in the Y direction? That is coming out, so that looks like a side force, right? So that's CYINI times QC times SW, right? And then finally, what is the force component in the Z direction? Well, that's this. That looks like CLINI times QC times SW, okay? Now, we've got to be a little bit careful about what frame this vector is expressed in. The way we've written it down here is this is expressed in, let's call this blue frame the tunnel frame. Okay, so I'm going to say FT is the tunnel frame. Okay, and I'm being very careful here because this is where the distinction between the tunnel and the wind is going to come in. So I can put this like such, the tunnel frame, right? If you're unfamiliar with this notation here of the superscripts or expressing vectors in different frames, right? Make sure you've watched our previous video where we talk about expressing vectors and rotating them from different frames. We're gonna leverage this pretty extensively over the next couple of corrections and discussions. So again, the video is this one right over here. You can get to it by the card in the upper right if you haven't seen that already, but I'm going to assume that you're okay with rotation matrices and expressing vectors in different frames and things like that, okay? All right, so let's come back to this. Now, here's the whole rub and why I've been kind of walking around the notation of what do I want to call this. Because if you think about this long enough, here's what the issue is. This here, in order to call this component, right, this value here is the force in the X tunnel direction. So the force that is straight back. I don't want to call that drag. The reason I don't want to call that drag is because what if the wind, you know, we made the assumption that the wind is coming straight down and the wind is aligned with the tunnel, right? What if that's not the case? What if the wind, I'm going to draw this in an exaggerated fashion, right? What if the wind, you know, it flows through, but for whatever reason, maybe just imperfections in the geometry of the tunnel, the way the airflow goes, but for some reason here at the model, what if the wind is more like this, right? Something like this. Right? What if the local velocity of the wind that hits the model is something like that, right? Well, what we actually have to do is the way drag is defined, right? Drag, aerodynamic drag in the wind axis is defined as parallel to the wind, right? So we really need another coordinate system, something like this, right? So this is, let's call this XWT. For the wind, the local wind in this tunnel frame, the local wind for this particular tunnel, right? So something like this, right? So now you have Z tunnel. And for now, let's make it, you know, this angle is what's sometimes referred to as your alpha upflow. right? To make this picture simple, right, you know, you could obviously say, okay, not just could it be hitting this at an upflow, but there could be a crossflow component as well. That's going to make this picture ridiculously difficult to draw, so let's just draw it with only an upflow, but with the understanding that it's also possible that this local wind vector, which actually hits the model, has some crossflow component as well, okay? So in this case, if you stare at this long enough, right, you have this alpha upflow here, right? Really, what we need is, I actually need the aerodynamic force, but I need this to be expressed in this this red frame, not the blue frame, right? So I need this expressed in the wind, I guess we're calling it WT, right? Okay? So the question is, what is this, right? Because the tunnel is going to report, it's going to give you a number here. It's going to give you 3 numbers. This first number is actually the force component aligned in the blue axis. The second component is the force component that's aligned with this similar blue axis. And same thing, this third one, it's the force component aligned with this Z blue axis, right? So again, I can't call that lift, or I can't call that drag, side force, and lift because they're not aligned with the wind. I need to rotate this vector here to be aligned with the local wind frame. Then I can call it lift, drag, and side force, right? So if you look at this long enough, right, you see we already have the F aerodynamic, right, expressed in this tunnel frame, right? So really what I need to do is I need to rotate this. I need to get some rotation matrix which goes from the tunnel frame to this local wind frame, right? And here, again, if you're staring at this and you're thinking about local wind frames and things like that, this is exactly also what we talked about in this previous video, right? Where we were talking about the difference between the body, stability, and wind frame, right? We talked about how you can rotate a vector through these, through an angle of attack and an angle of side slip to go from a body to a wind frame, or from a wind frame to a body frame, through this intermediate stability frame, all that kind of good stuff. So again, watch this video if you haven't already done so, because if you think about this, this is exactly the situation that we've got earlier. Now we can you can kind of think about this tunnel frame, right? This tunnel frame is almost like you know, as the body frame. You can think of this as a quote-unquote body frame, right? And then this W, this is the wind frame that we were discussing in the previous video, right? So really, this rotation matrix, we can actually make it through 2 separate rotations, okay? So what we're gonna do here is the rotation from let's do it this way, right? From the wind tunnel to the stability in this tunnel discussion here, right? This is rotating through the angle of side slip. This is our beta crossflow, right? And this is going to look like our 3x3 matrix where you got a cosine beta cross, a minus sine beta cross, and then a 0, and then I think you got the sine beta cross here, and then a cos beta cross, and then a 0, and then a 0, 0, 1, right? And then you could also have a rotation from this stability to the tunnel frame through the alpha upflow. And this was a rotation about the y-axis, right? So you got the 0, 0, 1, 0, oops, 0 like this. Then you got a cosine alpha up, minus sine alpha up, and then you got a sine alpha up, and then a cosine alpha up, right? So here are these 2 matrices. So we can basically multiply them together to get this guy, right? So I guess in general we would have what, the rotation matrix that goes from the local wind frame at the model, right, to the tunnel frame. This is now going to be a function of both alpha upflow and beta cross, and it's just the product of these 2 matrices, right? So it's CTST alpha up, right? That's this matrix times CSTWT beta cross. right? Let's just jam those two matrices together, okay? Great. So this we can now plug into here, although again we got to be very careful about the order of this. So it looks like I'm going to have to transpose this, right, to get it in the correct orientation. So, okay, if you do that, in fact, I'm lazy. I'm not going to do this by hand. I'm going to do this in Mathematica. Here's a screenshot of me doing this in Mathematica. And in fact, I'm also lazy. I don't want to write out the entire, well, maybe we should write it out. Yeah, sure. Let's write it out. And before we write it out, maybe I'm going to make one other note that we are playing a little bit fast and loose here. I should be rotating this force vector. In fact, that's exactly what we've written so far, right? And notice here that we renormalized all of these coefficients, but we renormalized from a coefficient to a force, right? By renormalizing through the dynamic pressure and the reference area, okay? That's the proper way to do it, right? You can rotate a force vector, right? Because this is a vector that you can draw. The reason I'm harping on this is this is going to come back, I don't want to say it's going to come back to bite us, but it's going to come back to something we need to worry about when we start thinking about rotating the moment coefficients a little bit later on down the road. But for now, what I'll say is you could, in this particular case, you could write this equation, but you could use just the coefficients. In other words, what I could write is I can still have this rotation matrix, 3WT, right, which is basically the transpose of this thing, times, and in here I'm just going to go CDINI, CYINI, CLINI, right? You could do this, and what this should get you, again, these are expressed in the tunnel frame. What this should get us at the end of the day is, this is really, I don't know how we want to write this, but this is now CD, I don't know, let's put a tilde on top of this, INI, CYINI tilde, and then a CLINI tilde, right? These are actually the force coefficients in the local wind frame, right? So this really is drag, this really is side force, this really is lift force coefficients, okay? So again, keep this in mind that I am shooting from the hip a little bit by neglecting this QC times SW, but since you can kind of see that it's just a constant factor for all of them, there's no problem to do this, okay? That is not true for when we talk about the moments later on down the road. So again, take me at my word right now that this is going to work, okay? And what we should do is let's write out what are these expressions by the time you do this entire matrix operation, right? And yikes, it's kind of long. Tell you what, give me a second. I'm going to erase the board. I'm just going to write it down so you don't have to watch me scrawling this off. And let's write down exactly what these are when you do this in Mathematica. All right, so here's what you get if you do that matrix multiplication. And again, if you don't believe me, here's a screenshot of me doing this in Mathematica, and that's where I got this expression, all right? And what this is doing, right, is again, this is correcting the initial lift, drag, and side force coefficients. It's correcting it for the potential of having an upflow as well as a crossflow in the test section, right? Now, let's look at the situation at the Kirsten wind tunnel. What is the values of alpha upflow and beta crossflow? So here's what's kind of interesting. I'll show you this picture here that is taken. These are the turning vanes at the bell mouth of the Kirsten wind tunnel, right? So again, remember these are the vanes that make the wind turn. It makes two 90-degree turns. So it comes from the fans, turns basically 180 degrees, and then comes down the test section. So look at these turning vanes. What's interesting about them is if you look at them, maybe scan your eye from the bottom to the top of one of these columns, notice that all of these turning vanes they're not all lined up. They're actually, each one of these is individually tuned, right? So what they've done is they've taken one of these turning vanes, they've tuned it, they've done a flow quality survey in the test section. Again, remember that paper that I referred you to earlier where they were running that 5-hole probe throughout the entire test section to try to identify what does the upflow and crossflow look like in the test section, right? And if that didn't look good, they would tweak these vanes a little bit, run it again, tweak the vanes, etc., etc. So it was a bit of an iterative process, but long story short, they did a really good job, and the upflow and the crossflow in the test section are actually very small at the Kirsten wind tunnel. So the last time I looked, I think at the KWT, I think we have a value of alpha of upflow is about minus 0.012 degrees. That's our published value, and our beta cross is actually 0. So there's no crossflow. Okay? So what's interesting about that is, does this simplify in this situation? For example, this beta crossflow of being exactly 0, you see, this actually knocks out a lot of these terms. So in fact, if you do that, what we can get is, let's write this over here. Maybe I'll write it like this. So this means your CDINI tilde, right? This term, if beta crossflow is exactly 0, right? This thing goes to a 1, 1, 0, right? So all this, it gets significantly easier, right? So this thing looks like CDINI cosine of alpha up, right, plus CLINI of sine of alpha up, right? And then similarly, your CYINI tilde, right, this becomes actually CYINI, right? That's actually nice. And then your CLINI tilde is going to look like CLINI cosine of alpha up minus CD sine of alpha up, right? Okay, now let's make this even easier, right? Notice at the KWT, this alpha upflow is a small angle, right? So why don't we small angle approximate all of these cosine alphas, sine alphas, right? So that means this becomes a 1, right? So actually I can just get rid of this. This becomes a 1. And let's small angle this thing. Let's just make this alpha up, right? So this is now times alpha up. And then similarly, this thing here, cosine, this goes away. Small angle, so this becomes just a 1, and this becomes a multiply, right? So here we go, small angle approximation. So this is even easier, right? Okay, so let's think about this. Let's keep thinking about this. So the correction on drag, it's the drag that is corrected for upflow is now the drag that was not corrected for upflow plus CL times alpha, right? Let's look at the lift. Lift is the uncorrected lift minus CD times alpha here, okay? Now, for most situations, right, I think you would agree that your, oops, I missed an INI here, right? So your CL is probably much, much greater than your CD, right? For an aircraft, you better be having you know, if you have a good aircraft, it's generating a lot of lift, right, to support its weight, and it's doing that with very little drag, right? So in most situations, this CL is orders of magnitude larger than this CD number, right? Would you agree? So this should be a very, very small number, right? Your drag should be small. So if you look at this, you got a small number times a small number. So its product is even smaller. So this, I think we can safely neglect. This is basically 0. Now this one, you have biggish number times a smallish number. So maybe that's actually not neglectable. So we should maybe leave that. So long story short, here's what's fascinating about this. After all of that rigmarole, right, we end up with this. And what is this saying? So this is your drag that is corrected for upflow and crossflow. This is your side force that is corrected for upflow and crossflow. And this is your lift coefficient that's corrected for upflow and crossflow. Again, sorry, I apologize. I'm kind of playing fast and loose with, I'm calling them drag, side, and lift, but really these are coefficients. And again, I'm harping on that point because it's going to matter later when we're talking about the moments, right? But long story short, these are the corrected values. They are equal to basically the uncorrected values, right? If you look at this, these are the exact same. These are the uncorrected for upflow and crossflow. The only place that we have a correction here, or a non-trivial correction at the cursor wind tunnel, is correcting your drag, right? And your drag is corrected by this, right? You take the uncorrected lift times the alpha upflow, right? So that's actually pretty darn interesting that really at the KWT, we should write this down, at KWT, this upflow and crossflow correction is only a drag coefficient correction. Right? That's a little hilarious, because after this entire discussion, all of these rotation matrices, yada, 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 actually what's applied at the KWT, it's just a drag correction. I guess there's no reason you don't keep all of the full trigonometric equations. I mean, I've got them here. Feel free to implement them if you really like to, but as you can see from this analysis, the only place it's going to make a non-trivial change is hopefully in your drag. Oh, and I guess also, not just drag, right? Also your angle of attack. We are going to correct the angle of attack as well. Do I have that here? Oh, shoot, did I forget to write that down? Well, here, I mean, no, tell you what, actually I saved that because we have to talk about wall correction. So tell you what, let's also make a slight note here that the alpha will be corrected. Because really, like we said earlier, right, the angle of attack, it's going to be the alpha that is the geometric angle of attack of the model, which is read by an accelerometer or an inclinometer or the pitch encoder or something like that. But that has to be, we have to add on this upflow due to flow angularity, right? So the actual angle of attack of the wind hitting the model, it's a combination of the geometric angle of attack plus the upflow, plus another correction that we're going to talk about next, okay? So let's punt on the alpha discussion, and we'll get a corrected angle of attack later. Okay, so yeah, let me think. That's pretty much what we wanted to talk about here. You can run through a very similar analysis with the moment coefficients, right? If you notice, right, all of this discussion was rotating the force coefficients to align with the local wind frame of the model. You can do the exact same thing. In fact, you probably should do the exact same thing with the moment coefficients. You'll see that actually the corrections are of a small order, and furthermore, there is another nuance with these moment coefficients that I keep alluding to, and I keep kicking the can down the road on that, and we'll talk about that in a couple of steps. So maybe keep that in the back of your mind, that if you really wanted to be complete and thorough, you could run through a very similar analysis here with the moment coefficients and rotate them to the local wind frame, so you really get roll, pitch, and yawing moments about the model moment center expressed in the local wind frame. But that's actually not done at the cursor wind tunnel. So really, all of this, like, this is an accurate statement. At KWT, this upflow and crossflow correction, the only way it works its way into force and moment data is it's literally just a correction on the drag of that magnitude there. Okay, so that is the flow angularity. So again, it's a little ironic that we spent 20 minutes discussing it, and and here's the result. Right? Okay, let's move on to our next correction then. All right, so now we're really cooking, and we're talking about wall corrections. This is actually very closely related to the upflow correction that we just discussed. So what's the idea with the wall correction? So let's take a look at this aircraft that's flying along in free air, right? This is the real condition that we want to have happen. And what I'd like to kind of sketch is some of the streamlines of what the airflow might look like over the aircraft in free flight. So, way out here at the way in front of the aircraft, it probably is straight, right? But now as the aircraft starts to influence the flow, before the wing, you actually get a little bit up, right? And then the idea is it comes down, right? There's downwash, right? That's the whole idea. That's kind of how an aircraft stays aloft, right? You can almost think of it as a momentum balance, where it is deflecting the wing, and the pressure distributions over it are deflecting airflow down, so you have a vertical component of momentum down, which will counteract the gravity and basically let you stay up. So anyway, long story short, you might have something like this, right? This is, again, the blue is the free air streamlines. okay? That's what it might look like. Okay, now let's contrast that with, maybe I'll draw another color. Let's look at what happens in the wind tunnel, right? The issue with the wind tunnel, right, is there are walls, right? There is a floor in the wind tunnel, and there's a ceiling in the wind tunnel in addition to the sides, but well, let's neglect those. Let's just look at these. So you see that this is clearly a problem, right? In the wind tunnel, you are not going to get the streamlines to look like free air streamlines. What are they going to have to do? They're going to have to do something along the lines of, you know, again, it will come in straight, you know, as you're coming down the test section, but it's going to start influencing it like this, right? And then the streamline is going to come down. It's still going to be deflected down, but then it's going to have to bend again, right, to become parallel with the floor. Right? So, long story short, what we end up with here in this configuration is that there is a delta angle of attack, right? So here's your, let's call this delta alpha WC for wall correction again, right? Oh, and sorry, I should have labeled this. The red is the wind tunnel streamlines, right? So this is the general idea, right? So the idea is that the angle of attack of the model in the wind tunnel is basically not representative, or not what it would be in real flight, right? So the question now is, what is the angle of attack? And if you stare at this picture, right, you can kind of see that in the wind tunnel, the angle of attack is actually lower than it should be in real flight, correct? So let's write that down just so that we're all on the same page, right? So the alpha, or the angle of attack in the wind tunnel, right, is smaller, right, slash lower, however you want to think of it, than it should be, i.e. what it should be in real flight, right? That's the concept. So what we're going to do is we're going to cook up a angle of attack correction. So this delta alpha wall correction, this is how much the angle of attack needs to be corrected. And what this is it's used as, you got a term del W times the quantity S wing over C times CL wing. Okay, so in this case, let's just define some of these symbols. So del W is a correction factor, and it's typically greater than 0. So this is a correction factor. This is, again, sort of one of those fudge factors that basically tell us how much are the walls of the wind tunnel bending the streamlines and therefore affecting the angle of attack, okay? SW is the area of the wing, right? C is the cross-sectional area of the test section without, or let me see, yeah, without fillets. Right? Okay, and then, oh crap, I ran out of room. Here, CLW. This is the lift of only the wing. Or I guess, technically, I guess it's a coefficient of lift of only the wing, right? So let's look at this formulation. And again, I'm not a fluids person, or I didn't derive this correction. I just want to present it, and let's talk about it to make sure it makes good engineering sense, right? So, SW, obviously that makes sense. It's the area of the wing. As the wing gets bigger, right, the bending that you're going to see, this effect, this wall correction problem, is going to be exacerbated, right? So that makes sense that as the wing gets larger, right, the magnitude of this correction gets larger as well. Similarly with CL wing, right, you see that the amount of bending that occurs due to the wings, due to the walls, is directly related to how much lift you're generating, right? If you're generating more lift, if the wing, again, this is the wing only, that's CLW, right? If the wing is generating more lift, that means it has more downwash. Therefore, this wall is making the problem worse, right? So we see that, again, that makes sense. Both the size of the wing and the amount of lift that is generated by the wing, those end up in the numerator. So as those go up, this alpha wall correction also has to go up. And again, we see this thing in the denominator. So as your test section gets bigger, right, it mitigates the effects of this, because if it's bigger, right, the walls are farther away, it's not influencing the streamlines as much. So again, all of this makes sense. And similarly, the reason why this is typically positive, right, is because this is what we just talked about, right? The angle of attack in the wind tunnel is smaller than it should be. So this correction should probably be positive, so we can increase or bump up the angle of attack, right? So therefore you have positive, 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 positive. All these are positive numbers. So this delta alpha wall correction is, again, typically a positive number, right? Now, the other thing that we might want to talk about here is, notice that again, CL wing, right? What you have to do in order to compute this correction, right, you need to get the coefficient of lift of just the wing only, right? Because like we said here, the wing is what's causing the majority of the downwash, and therefore the majority of the contributions to this effect. So the thing you might have to think about though is, how are you going to get CL wing, right? So the question should be like, more importantly, what contributes to CL, right, to the overall CL of the overall model, and therefore we can ask a similar question then of what contributes to CL wing, right? Now, if you think about this long enough, you can say, what are the differences between these, right? The lift of the wing and the lift of the entire model. Well, just look at the picture, right? You got the wing and then the rest of the model. What's on the rest of the model? You can say like the fuselage. Yeah, the fuselage generates a little bit of lift, so I don't know. That's probably it's negligible. All this stuff, the only thing that contributes significantly, I would argue, to the lift of the overall model is this horizontal stabilizer, right, is usually fairly large. You know, it's non-trivial, right? It has to be big enough so that you have pitch authority. So most aircraft designers will make this horizontal stabilizer, you know, a reasonable size. So therefore, I think it's reasonable to say that the majority, you know, of the lift of this entire model, you've got lift from the wing, and you also have lift from the tail. And again, like we said, yeah, you got lift from the fuselage, lift from the nacelles, the landing gear, whatever, but all that stuff is small. These two, I think, capture the majority of the lift, okay? So what this means, though, is that the lift of the tail is non-trivial, right? So in order to isolate CL wing from CL, what you actually have to be able to do in the wind tunnel is you want to be able to remove the entire tail of the horizontal stabilizer of the aircraft, right? And then what you can do is you can run an entire run without the tail on. That should allow you to measure just the lift of the wing, right? So what's interesting about this is, in order to apply this, in order to get CL wing, right? So to get CL wing, you have to run a config without the horizontal stab installed. Okay? This is sometimes what's referred to as a lift set. Okay, so for a given configuration, you might have to pop off the entire horizontal stabilizer so that you're able to get this parameter CL wing, so you can understand how does CL wing vary with angle of attack, right? So that's interesting. Again, something you got to think about as you're designing a wind tunnel test, and more specifically designing your wind tunnel model. You may need to make sure that your wind tunnel model has the ability for that horizontal stabilizer to just pop off, and then you can run the model and just the wing by itself, right? Again, this is a similar issue with the strut and interference, the tare and interference that we were talking about earlier. In order to do this, you need to now run a completely second run. You need to run a tail on and a tail off configuration. So that's two data sets that you got to run. That's two separate runs you got to make. You have to come down in between for a model change in order to pop the tail off. Again, we're talking time and money and effort to do this. So you don't want to do this for absolutely every single configuration, right? So you may want to think about getting a lift set for a critical configuration again, like for like some baseline configuration. And then if you change like the ailerons, right, the deflection angles, or you change the elevator deflection angles, maybe you say that, I'm just going to apply this same lift set because the lift of the wing doesn't change that much, right? Now, however, what about flaps? You might need a lift set for no flaps, and then a flaps down 10, flaps down 15, because I would argue that flaps, you know, if you do make a configuration change such as flaps, that probably does change lift of the wing significantly, right? That's the whole point of flaps, is that you want to increase the lift of the wing. So as a test engineer, you got to be a little bit smart about which model changes or which configuration changes warrant running another tail off run so that you can generate another lift set. So the idea is you may need to just have a library of lift sets in your back pocket for critical configurations where lift of the wing changes, and then for any other subsequent runs, you just pick the lift set which most closely matches the configuration of interest, right? Okay, so I think that's a good discussion here on the lift sets and all this. So at the end of the day, what we end up with here is we have an angle of attack change is the effect as this effect of having the walls, right? You have the walls in the wind tunnel, therefore it changes the angle of attack of the local airflow at the model. Is that ringing a bell? That should ring a bell. In fact, the correction we just talked about previously of this with upflow, right? That's the exact same problem, right? We were talking about. We said that the upflow means that the angle of attack of the model is slightly different than what we expected. This is exactly another case of this, right? It's just a different reason that the angle of attack is different, and it's a different magnitude, but the idea is the exact same. So really what we can do right here is we can say this is the same as the alpha upflow correction that we just did earlier. Correction. So we could run through the exact same logic we did earlier, right? We could do all those rotation matrices to get us from one frame to the other local wind frame by correcting through this delta alpha wall correction. We can go through all that subsequent analysis, and we saw last time that all of that bought us was a drag correction, right? That's all we ended up doing. So this is the exact same situation. So here, what we've got is all of this discussion via the same thing. So I'm just going to draw this as an arrow. And again, this arrow is basically apply the same logic that we applied in our upflow correction, except now instead of alpha up, you're using delta alpha wall correction, right? That's the local change in angle of attack. So like we said, all this means is that you now generate a delta CD due to wall corrections, right? And this thing looks like the angle times CLINI, right? That's what we ended up last time with. So that's pretty darn fascinating that right now in terms of correcting the forces, the only thing that's different due to the wall corrections is again a drag correction. Now I say forces because the moments is actually a slightly different story that we also have to take into account. So tell you what, give me a second to erase this. We'll keep that picture and let's talk about the moments now. All right, so the way that the moment correction due to wall corrections comes into account is if we examine the horizontal stabilizer and in the rear of the aircraft. I'm gonna call that out because keep in mind, right, what if this was a canard and it was something in the front? But for now, let's look at a conventional configuration where you've got the horizontal stabilizer in the empennage in the rear of the aircraft. Now, this streamlining discussion that we just had, we could kind of do the exact same thing. So again, in free air, like let's look at what the streamlines might look like that are hitting the tail, right? It might be something like this, right? The blue was the free stream, and again, the red was our wind tunnel streamline, something like this. Okay, so now what's interesting again is you look at this, you have like a delta alpha tail wall correction, right? And what's interesting is if you look at this, look at the red and the blue here on the tail versus the red and the blue at the main wing, right? The main wing here is what we consider sort of your traditional angle of attack. This is like the angle of attack of the tail, right? So in this case, right, the angle of attack of the tail, right, in the wind tunnel, it's actually larger or higher than it should be. So again, let's write that down over here because it's the exact opposite effect. So the angle of attack of the tail, right, in the wind tunnel, it's actually the opposite, right, is larger slash higher, however you want to think about it, right, than it should be, right, versus compared to free air, right? So there's a couple of effects of this. One effect of this, right, is that the lift of the tail is different than what it should be in free air, right? Now, that being said, that's kind of, well, let's call that negligible, right? Because we know, sure, the tail generates non-trivial amounts of lift, right? But this angle of attack is going to be small. The lift of the tail is way overshadowed by the lift of the main wing. So I think if we neglect the change in the lift of the tail due to this delta alpha wall correction, I think that's a reasonable approximation, right? However, what's the whole point of having a horizontal stabilizer like this, right? You have this rear horizontal stabilizer and it's offset from the center of gravity of the vehicle by a non-trivial moment arm, right? So it basically gives you a pitching moment, right? That's the whole point of having a tail or having an elevator back here, is you have large pitching moment authority from this tail. Now, that is going to be non-trivial, right? Because sure, there's a delta lift of the tail, so there's a delta force times a large moment arm, so there's a delta pitching moment here. So there's basically a pitching moment correction that we have to apply because the pitching moment that we measure in the wind tunnel is different than what it should be in real life. So the question is it too much or is it too little, right? So I don't know, we can draw this, let's draw the CG of the aircraft like this, right? So here's a CG of the aircraft. I'm just going to look at just a CG, I don't know, like make it up, say it's over here, right? Here's a CG of the aircraft. Okay, so in the free air, let's draw the tail, right, at some angle of attack. So here's your free air or free condition, right? And this thing has some pitching moment, right? Right? Now, if we look at this in the wind tunnel, right, the same thing, a very similar situation. Now, what we said is that in the wind tunnel, the angle of attack of the tail is larger than it should be, right? So the tail, you can kind of think of it something like this, right? The angle of attack of the tail is larger. So here is the wind tunnel, right? So again, the way you can think of this, right, is that this higher angle of attack, right, is going to tend to put like a nose down. So I drew a positive, right, this is a positive pitching moment here as somewhat large. So you can almost think of it as like this, right? So the pitching moment, the positive pitching moment should be smaller, right, due to this angle of attack, right? So really what we're saying is that in the wind tunnel, the pitching moment that you are measuring, it's too small, right? The pitching moment, we need to bump it up to make it a bigger pitching moment to account for this fact of this delta alpha tail, right? Long story short, we need a positive pitching moment to be added to whatever the balance measures, right? Okay, so the way we're going to do that is we're going to apply a correction. So here's your delta pitching moment, Cm, due to the wall correction, okay? So this is going to be given as, again, there's a fudge factor of delta, it's called delta AS, right? Times this partial, which we're going to call DCM DDS, is sometimes what it's referred to, but really it's just a partial. And we'll talk about it in a second here. Times CL wing times SW over C. Okay, and then again, well, let's say this thing, this delta AS, this term is, again, it's usually it's this fudge factor which is positive. Okay, so now let's talk about some of these other terms, like this thing, right? This partial Cm with respect to a delta stabilizer, okay? This is sometimes referred to as, you might hear this called DCMDDS, right? Here's the DCMDDS, right? And again, it's just, if you look at it, literally, it's the partial, it's telling you how sensitive is the pitching moment coefficient to a change in stabilizer angle, right? Okay, so this is effectively telling you how effective is this particular tail configuration at changing the pitching moment, right? We already talked about what CL wing was, right? That's the lift of just the wing. We already know what SW and C are from this other term. In fact, it's very darn similar, right? If you look at, actually, gosh, yeah, this component is the same as this component. So it's got the same sort of bones or the feel for where that comes from, right? The more lift you're generating with a bigger wing, the more you have this the bent streamlines due to the wind tunnel wall, so the more you've got to correct it, right? Now, what is this DCM DDS? Let's get a better idea of this. This again is the change in pitching moment to a change in stabilizer angle, right? So as you know, typically if you were to change the stabilizer angle by a positive amount, right? That's sort of like this situation, right? By increasing the stabilizer angle, right, you actually decrease the pitching moment. So this term is usually negative, right? Would everyone agree, right? So let's take a look at this. This is a negative number, positive number, positive number, positive number. This is a positive number, but you hit it with a negative. So overall, by the end of the day, when you multiply all this thing, this delta CM wall correction is typically positive for most configurations, which again makes sense because what we want to do is we want to add this pitching moment on to our correction, because what we see here, the pitching moment in the wind tunnel is too small, right? So we have to add a positive number to that pitching moment coefficient to bring it up to what real life should be, or what free air should be, right? So this is actually kind of interesting. So the other thing we might want to ask here is where are you going to get some of these numbers, right? Okay, fine. We can get CL wing from tests, from lift sets, right? We already talked about that earlier. You can get SW from CAD or geometry. You already know what the cross-sectional area of the test section is. This partial is kind of interesting. This you can also get via direct testing, okay? The way you get this is, if you think about this long enough, right? I think everyone would agree that a partial derivative, right? DCM d delta s, right? You can approximate this gradient or this partial, right, using a finite difference, right? You can look at a change in CM over a change in delta stabilizer, right? And isn't this the same thing as basically saying you take CM at some condition 2 minus CM at some condition 1 all over a stabilizer at condition 2 minus the stabilizer at condition 1? Right? So literally what you're going to do here is you're going to collect enough data to get this finite difference. All this really means, if you think about it long enough, is it just means you fly you do a run of the aircraft with the horizontal stabilizer at a given angle, right? Then you're going to repeat that entire run, but what you're going to do is you're actually going to change the angle of this stabilizer. You're going to literally have to take the entire horizontal stabilizer and increase it by 2 degrees or something like that. And then you run that whole nother run again, right? And then maybe for good measure, you tilt it down at -2 degrees and you run it again. If you do that, you can get the sensitivity of how is the pitching moment for this given configuration sensitive to a change in the stabilizer angle. So this is actually fascinating because, again, this brings up something that you might want to think about. If you're the wind tunnel engineer or the designer of this test, you're designing this model, writing requirements for your vendor to build you this model. If you want to conduct and apply this type of a correction in your wind tunnel test, you better make sure that your model has the ability to change the entire stabilizer angle through some range of angles, right? And if you do that, you can run these tests, you can get your DCM DDS, therefore then you can plug it into your pitching moment wall corrections and you'll be off to the races, right? So, yeah, that is that's pretty much what's interesting about this. So again, what we've got now is the pitching moment correction. Where do I have this? Right. So you compute this pitching moment correction and then, shoot, I kind of ran out of board space. But anyway, now your pitching moment, right, your CM, where did I have this thing? Oh yeah, okay. Your CM in the wind axis, it's basically going to be your CMINI, right? And again, these are about some model moment center, right? And then you're going to add on this delta CM due to the wall corrections, right? So here is the only change in a moment coefficient that we are going to correct for at the Kirsten wind tunnel due to wall corrections, right? Now, before we leave this concept of wall corrections, you might want to think, do I always want to apply wall corrections? And the answer is no. There are some configurations where you do not want to apply wall corrections. For example, I've got a picture of this over here. This contraption that you see is what's referred to as a ground plane. Okay, so in some wind tunnel tests, this is literally a surface that you bring up and put it close to the bottom of the model, right? And then you would do some runs with this configuration. You might ask yourself, why in the world would you want to do that? You know, again, here's an example of a model installed with this ground plane, right? If you think about this long enough, right, this is an excellent test of an aircraft and its behavior in sort of takeoff and landing situations where you are literally coming in close to the ground, right? Have you all heard of ground effect before, right? Ground effect is exactly this here, right? So ground effect is when you are close to the ground and the streamlines are bent due to the presence of the ground, you get significant changes in the aerodynamic force and moment data, right? And the behavior of the aircraft. So if you're trying to characterize takeoff and landing performance of the vehicle, right? You do not want to apply these wall corrections because you're trying to test and characterize and quantify the effect of literally having the ground near the aircraft. So you want to keep those effects in your data. You don't want to tear them out. So if you're installing a ground plane and doing this type of testing, make sure you tell the wind tunnel that, hey, this is a run for takeoff and landing. Do not apply any of these corrections that we just talked about for wall corrections, right? Because I want the wall in there. It's the whole point of putting in the ground plane and doing this test, right? Okay, great. Let's keep rolling. I think we're almost to the end of this list. All right, so here we are, second to last step. We have finally done enough corrections to obtain our final coefficients and corrected angle of attack. So here they are. Here's our final coefficients expressed in the wind axis. And again, this is now the actual true wind axis, right? Relative to the local wind that the model is being subjected to, right? So the coefficient of lift expressed in the wind axis, again, there's no correction. That's the same thing as our initial coefficient we did, several steps back. But drag, we see the final drag coefficient that we're going to report from the wind tunnel. It's going to be that initial drag coefficient, but then we've got a change, a delta CD due to the tunnel flow, upflow angularity change, and we've got a delta drag correction due to the wall corrections, right? So drag we see is somewhat different, right? And again, that is very important because usually drag is one of the things we probably care quite a lot about, especially if you're an aircraft performance guy, right? You want to make sure that that drag is as low as possible. So, you know, a couple of counts actually matter, right? So we want to make sure that this is corrected at as close as possible. And we don't really care so much about the side force. The side force, the final side force is basically your initial side force coefficient, okay? The pitching moment is just corrected for wall corrections, right? As we just talked about, whereas the roll and the yawing moment, those are uncorrected. So interestingly, in your force and moment, aerodynamic force and moment data that you get from the wind tunnel, really it's the drag and the pitching moment have some interesting effects and corrections applied to them. Okay, now the other thing we really care about from the wind tunnel and from an aerodynamic perspective is the angle of attack, right? So the angle of attack, it's going to be the indicated angle of attack. Again, this is what's measured by your accelerometer or your encoder or what have you. But then we have an angle of attack correction due to the upflow in the tunnel as well as the wall corrections, right? And then finally, for the sake of completeness, to kind of round out all of the information that we really care about and need for our aerodynamic force and moment data, remember we also talked about earlier in one of our previous corrections, how we corrected the dynamic pressure that the model subjected to. So it's going to be the actual dynamic pressure, which again, this was the indicated dynamic pressure from the static pressure strips that we measured, which was corrected for QA to QI, but then we also correct for blockage here, both due to the model as well as the wake. So there you have it. We did all of this work. And on this one page is basically kind of our final aerodynamic force and moment data, as well as angle of attack and dynamic pressure. So again, this is pretty much the whole shebang. That being said, we still need to take one more step, and because all of this data that we presented right here, remember, this is in the wind axis. So that's what all this WA subscript is trying to denote. So all of this data is in the wind axis, and usually that could be totally fine, right? You can hand that off to your customer and they can take this and then they can do some transformations if they need. Me personally, myself, I'm a GNC engineer, so I actually don't want data in the wind axis. I would want this in the body axis so I can apply this to my my dynamic aircraft simulation or things like that. So the last thing that we need to do is rotate or express this data in a different frame. All right, so the absolute last thing that we might want to do with this wind tunnel data is basically transfer it to another axis. So remember, what we did previously was we obtained the force and the moment data expressed in the wind axis, right? So now let's think about rotating that to the stability axis. So here's that SA stands for stability axis, and remember earlier we had all the wind axis terms, right? So to get the, let's break this down very carefully and very slowly. To get from the wind axis for the force coefficients, right? So that are these ones right here, okay? So if you look at this, this is actually, again, it's pretty much a standard rotation from the wind axis to the stability axis. Again, you got to be a little bit careful with how you define positive drag versus the positive x-axis for your wind and stability axis. So again, the nitty-gritty details are here in the notes if you want to see all the calculations, but this is literally pretty much just accounting for that, expressing the aerodynamic force vector in the wind axis, right? And then rotating it to the stability axis, right? So that's what you end up with here, right? And this looks fairly standard, right? Now, let's be a little careful now. We want to do a very similar operation with the aerodynamic moment coefficients, which are these three bottom ones. Now, again, that all we're doing is we are rotating the aerodynamic moment vector from the wind axis to the stability axis. Now, note I said it's the aerodynamic moment vector, not the aerodynamic moment coefficient vector, right? That one adjective, that coefficient descriptor versus just the moment by itself is extremely important. We should maybe write this down, right? Really, we should say you can only rotate the aerodynamic, or actually not even aerodynamic, any force and moment, right? A force and moment vector, right? Notice the word coefficient is not in there at all. The reason why I'm making that distinction is you got to remember way back several steps earlier when we were generating these initial coefficients, I told you keep in mind the fact that for the aerodynamic moment coefficients, the reference length that is used at the Kerstin wind tunnel and used at many other wind tunnels and used in different applications, they could be different. Remember, the pitching moment coefficient was normalized by C bar, whereas the roll and the yawing moment coefficients were normalized by B ref. So what that does, right, is that it makes it so the moment coefficient vector, right, if you were to stack up, let's think about this. The x-axis, this is like a C roll, right? And then the y-axis, this is C pitch, and then C yaw, C end, something like that. And there might be negative signs on some of these again to align, but you got to be careful. If you put these three quantities on top of each other, this is not a vector that you can rotate. The reason being is because this thing came from the rolling moment, the pitching moment, and the yawing moment, right? This is a vector. These three quantities, you can draw that vector in space, and you can talk about expressing or rotating that vector to different frames. However, this process of going from an actual moment to a moment coefficient, this process, it had a C bar or a B ref, depending on which element you were working with. So in effect, these two vectors are, I gotta be careful, I shouldn't call them, this three tuple and this three tuple are not even pointing, they're not pointing in the same direction, right? One of them has been scaled or skewed in an odd way due to the fact that C ref or C bar versus B ref was being used. So again, I'm just harping on this point because this is where you get some of these odd terms that I'm gonna maybe circle here in red. Here. This B ref over C bar, and over here you see the opposite. You see a C bar over B ref. That's where this comes in, because what you need to do is, if you want to rotate the aerodynamic moment vector from the wind axis to the stability axis, what you have to do is you have to take the aerodynamic moment coefficient vector expressed in the wind axis. That's what we got in our last step with our final coefficients. You need to first normalize this thing up to a aerodynamic moment vector in the wind axis. Then you can rotate that moment vector from the wind axis to the stability axis, and then you need to renormalize again using C bar or B ref as appropriate. That's where you get these mixed terms in here. So again, I just want to be a little bit careful. Again, the nitty gritty is in the notes, but just that's the concept, and I guarantee you someone is going to mess this up. Someone is going to neglect this or try to rotate this vector right here directly without taking this into account, and you're gonna introduce errors here, right? So again, just be a little bit careful that this is a very easy pitfall to fall into. In fact, some other tunnels that I've been to get around this problem, they normalize all of their moment coefficients by the exact same reference length. They don't, you pick C bar or B ref, pick one or the other. Don't have this mix matched usage of reference lengths when you're normalizing to aerodynamic dimensionless moment coefficients, right? Okay, long story short, that's what you end up with, right? So again, this at a very high level conceptually, all it is you're taking the aerodynamic force vector, rotating it from the wind axis to the stability axis. You are also taking the aerodynamic moment vector, rotating it from the wind axis to the stability axis, right? Okay, and if you buy that, going from the one more frame over to the body axis is not much more difficult. It's just we need to now also rotate over the angle of attack alpha here. So for completeness, here's a set of equations to do that. So, wow, all right, I think that is it, right? Because at this point, we have taken the data that we acquired from the wind tunnel. We've gone through pretty much every step of the data reduction process to obtain this. Again, like me as a GNC engineer, this is what I want. I want the aerodynamic force and moment coefficients expressed in the body axis about whatever XX model moment center that I want. So this is the data that I can now take that hopefully represents a full-scale free flight aircraft, and I should be able to use this now in for example, like a dynamic simulation of the aircraft, so I can see how it's going to behave, start thinking about building control systems around it, start thinking about trimming, linearizing, all that kind of good stuff. This is the data that is going to feed into that simulation, right? So, wow, at the end of this entire discussion, we finally got there. This is it. All right, so before we wrap up today, I just wanted to leave you with a couple of extra references in case you're interested in learning more. So the first one of these references is obviously the Kirsten Wind Tunnel website. I would highly recommend going to this URL. So if you come here, you'll see that there is a ton of information and history and lots of other resources here on the website. For example, there's a technical guide to the Kirsten Wind Tunnel. So this, you can actually request this document, and it has a lot of the data reduction procedures and processes that we talked about today. There's also a lot of great things in the download section. You'll find things like some suggestions on how to design your wind tunnel model, as well as additional diagrams that might supplement some of the discussion that we had today. So again, this website is a great resource for additional wind tunnel testing and Kirsten wind tunnel specific information. Obviously, the other two great resources were those two papers that we talked about and covered that document some of the flow quality as well as some of the simplified corrections that are applied during the data reduction process. And then finally, one excellent resource is this book by Barlow, Ray, and Pope. So this is the low-speed wind tunnel testing, and it's kind of considered the de facto standard of finding references and additional discussions and additional data reductions and considerations you may want to investigate while looking to conduct a low-speed wind tunnel test. So again, these are just some great references to check out, which actually cover most of the material that we talked about today. So I would highly recommend looking at some of these public documents. So, with that being said, I think we want to leave it here. Keep in mind, the discussion we had today was, you can almost think of it as reducing a single data point, right? You take one point of data, and we talked about all of the processes that you need to do to get it reduced to final coefficient form. In our next video, we are now going to look at, well, what do sweeps of data look like? What should you expect to be seeing out of a wind tunnel test? What should this aerodynamic force and moment coefficient data look like, right? And we'll also wrap up this discussion on wind tunnel testing, and you can kind of see why we broke it up into three different parts, because it's a fairly large topic, right? In fact, I think I wouldn't be surprised if this video ends up being one of the longest videos I've got on the channel. But again, it's long because I'm very excited. It's a very interesting topic to study, and I think it yields fascinating data. It's a really interesting way to get aerodynamic data for an aircraft or for some other type of configuration, right? Okay, so with that being said, I think this is a good spot to leave it. I hope you enjoyed the video, and if so, I also hope you'll consider subscribing to the channel. Surprisingly, if you just scroll a little ways down and click on that subscribe button, it really does help me continue making these videos. And remember, speaking of the new videos, the new ones come out every Monday, so I hope I will catch you at one of these future discussions and we can all learn something new together. So until then, I think I'm going to sign off. Talk to you later. Bye.